Hello there, and welcome to the Sleepy Science channel. Tonight, we'll be exploring the quiet, hidden world beneath our feet and all around us. A realm of fungi, mysterious networks, and silent transformations. These organisms are neither plant nor animal, yet they shape the world in ways we're only beginning to understand. They grow in darkness, connect entire forests, and transform death into life. The kingdom of fungi is both familiar and strange, something we encounter every day, yet rarely pause to consider. If you enjoy these quiet explorations, I invite you to like and subscribe or share a simple thought down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the calm of the fungal world to carry you. Let's begin. Fungi belong to their own kingdom, separate from plants and animals. For centuries, people assumed mushrooms were simply odd plants, vegetables that grew in the dark. But scientists eventually discovered they were something entirely different. Fungi form their own kingdom of life, as distinct from plants as animals are. They cannot photosynthesize like plants do. Instead, they must absorb nutrients from their surroundings, breaking down organic matter or forming partnerships with other organisms. Their cells have walls made of chitin, the same material found in insect exoskeletons, rather than the cellulose of plants. This places them in a unique position in the tree of life, closer to animals than to the green world we walk through. When you see a mushroom pushing through forest soil, you're witnessing a member of an ancient lineage, one that has existed for over 1 billion years, quietly shaping ecosystems in ways we're only beginning to understand. The mushroom, you see, is just the fruiting body of a vast hidden network. When you spot a mushroom in the woods or growing on a lawn, it's easy to think of it as the entire organism. But that visible mushroom is just a small part of the story. Beneath the surface lies an enormous network of thread-like structures called hyphae. These microscopic filaments weave through soil, wood, or whatever substrate the fungus inhabits, forming a mass called mycelium. The mycelium can spread for acres underground, far larger than the mushrooms it produces. Think of the mushroom as merely the fruit of an apple tree, a temporary structure created to spread spores. The real organism, the living network, remains hidden below, patiently growing, absorbing nutrients, and waiting for the right moment to fruit again. Some mycelia can live for thousands of years, making them among the oldest living things on Earth, though we rarely see them. Mycelium can spread across entire forests, connecting thousands of trees. In forests around the world, a hidden network pulses with life beneath the soil. Mycelium doesn't just surround individual trees. It connects them, tree to tree, species to species, forming what scientists call the wood wide web. These fungal networks attach to tree roots, creating partnerships where both organisms benefit. The fungus receives sugars from the tree's photosynthesis. While the tree gains access to water and nutrients, the mycelium gathers from the soil. But the network does more than just feed individual trees. It allows them to communicate, sharing resources and even warning signals about disease or insect attacks. A mother tree can send carbon to her shaded offspring through these fungal highways. Sick trees receive support from healthier neighbors. The forest, it turns out, is not a collection of individuals competing for survival, but a cooperative community, bound together by fungal threads, invisible and ancient. Some fungal networks can cover thousands of acres underground. The mycelium of certain fungi doesn't stop at a few trees or a small grove. In some cases, it spreads across thousands of acres, forming one of the largest organisms on Earth. In Oregon's Blue Mountains, a single honey fungus, Armillaria solidipes covers over 2,000 acres and is estimated to be thousands of years old. This vast organism grows slowly, spreading through the forest floor, its hyphae branching and reconnecting in endless patterns. From above, you would never know it exists. You might see scattered mushrooms, small golden clusters appearing each autumn, but beneath your feet lies a living network larger than many cities. These massive fungi remind us that size and significance don't always reveal themselves to the eye. The largest living things on our planet are often invisible, working quietly in darkness, shaping ecosystems without fanfare. Fungi can digest almost anything organic, from wood to plastic. Fungi are nature's great recyclers, capable of breaking down substances that almost nothing else can touch. Their mycelium secretes powerful enzymes that dissolve complex organic molecules, turning dead trees, fallen leaves, and animal remains into nutrients that other organisms can use. Without fungi, forests would choke on their own debris, and the carbon cycle would grind to a halt. But fungi don't stop at traditional organic matter. Some species have been found breaking down plastics, petroleum products, and even radioactive materials. Scientists are studying these remarkable decomposers, hoping to harness their abilities for environmental cleanup. In contaminated sites, fungi might offer solutions where other methods fail. They work slowly and quietly, their hyphae spreading through toxic soil, transforming pollution into harmless compounds. The same organisms that rot a fallen log might one day help heal our damaged planet. The oldest known fossil fungi date back over 1 billion years. Fungi have been shaping Earth for an almost incomprehensible length of time. Fossil evidence suggests they emerged over 1 billion years ago, long before the first animals walked on land, before even plants colonized the continents. These ancient fungi likely lived in water or in association with early algae. As life moved onto land, fungi came too, possibly even helping plants make that crucial transition. Early land plants lacked true roots, and it's believed they formed partnerships with fungi to gather water and nutrients from the soil. This ancient cooperation may have been essential to greening the planet. Over hundreds of millions of years, fungi diversified into countless forms, from microscopic yeasts to giant mushrooms. They survived mass extinctions, adapted to every environment, and continued their quiet work of decomposition and partnership. When you see a mushroom today, you're looking at the descendant of organisms older than almost any other form of visible life. Fungi helped plants colonize land millions of years ago. The world was once barren rock and water, a place where only the simplest life existed. Plants lived in the oceans, and the land remained empty. But around 470 million years ago, something changed. Plants began to appear on shore, and scientists believe fungi made this possible. Early plants were small and lacked the complex root systems modern plants have. They needed help gathering water and nutrients from the rocky, nutrient-poor soil. Fungi provided that help. By forming partnerships with these pioneer plants, fungi extended their reach into the ground, acting like external root systems. In return, the plants shared the sugars they made through photosynthesis. This ancient collaboration allowed life to spread across the continents, transforming Earth's surface from barren stone to green forests. Every forest, every garden, every blade of grass owes its existence in part to that ancient fungal partnership, a relationship that continues to this day. Mycorrhizal fungi form partnerships with most land plants. Walk through any forest, any meadow, any garden, and you are surrounded by invisible partnerships. Mycorrhizal fungi attach to the roots of most land plants, forming symbiotic relationships that benefit both organisms. The fungus wraps around or even penetrates the plant's roots, greatly expanding the surface area available for absorbing water and nutrients. In exchange, the plant provides the fungus with sugars created through photosynthesis. This arrangement is so common that over 90% of land plants depend on it. Without mycorrhizal fungi, many plants would struggle to survive, unable to access enough phosphorus, nitrogen, or water from the soil. These partnerships are ancient, evolved hundreds of millions of years ago, and they remain essential to the health of ecosystems worldwide. The next time you admire a towering tree or a blooming flower, remember that hidden beneath it, fungal threads are working tirelessly, feeding the roots, connecting the plant to a larger network, supporting life in silence. Some fungi can glow in the dark with a soft bioluminescent light. In certain forests, if you visit on a dark, moonless night, you might witness something magical. A soft, ghostly green glow emanating from decaying wood or scattered across the forest floor. This is bioluminescence, produced by certain species of fungi. More than 70 species are known to glow, creating what some call foxfire or fairy fire. The light comes from a chemical reaction within the fungus, similar to the glow of fireflies. Scientists believe the light may attract insects, which then help spread the fungus's spores, or it might simply be a byproduct of the organism's metabolism, with no particular purpose. Whatever the reason, the effect is enchanting. Imagine walking through a dark forest and seeing faint, glowing patterns tracing the shapes of fallen logs, like nature's nightlights. These glowing fungi remind us that even in darkness, life finds ways to shine, quietly illuminating the hidden corners of the world. The glow can be bright enough to read by in complete darkness. While most bioluminescent fungi produce only a faint shimmer, some glow brightly enough to be genuinely useful. Historical accounts tell of travelers using glowing wood as makeshift lanterns, and during wartime, soldiers reportedly used foxfire to read maps at night, without revealing their position with a flame. The light is gentle, not harsh, a soft, greenish glow that seems almost otherworldly. If you gathered enough glowing fungal material, you could indeed read by its light, though the pages would be bathed in an eerie luminescence. This natural light is cold, producing no heat. Unlike fire or electric bulbs, it is pure biochemistry, a molecule breaking down and releasing energy as visible light. To imagine reading by fungal glow is to touch something primal, a connection to the way humans once relied on the natural world for even the simplest needs. In an age of electric lights, these glowing fungi feel like relics of a quieter time. Fungi can survive in extreme environments, from deserts to the Arctic. While we often associate fungi with damp forests and decaying wood, they are far more adaptable than that. Fungi thrive in the driest deserts, the coldest polar regions, and even the most hostile environments on Earth. Some grow on bare rock, slowly breaking it down over centuries. Others endure freezing temperatures, lying dormant through long Arctic winters before springing to life in brief summers. In deserts, fungi form crusts on the soil surface, helping to stabilize sand and prevent erosion. In the depths of the ocean, near hydrothermal vents, fungi have been found living in conditions once thought impossible for complex life. They even grow inside nuclear reactors, feeding on radiation. This adaptability speaks to fungi's ancient resilience. They have weathered every climate shift, every mass extinction, and every environmental challenge Earth has thrown at them. Wherever life persists, fungi are there, quietly decomposing, partnering, surviving. Some fungi have been found growing inside the Chernobyl reactor. In 1986, A catastrophic accident at the Chernobyl nuclear power plant released massive amounts of radiation, creating an exclusion zone deemed too dangerous for human life. Yet life found a way. In the years following the disaster, scientists discovered something astonishing. Fungi were growing on the walls inside the damaged reactor, thriving in radiation levels that would be lethal to most organisms. These fungi contain high levels of melanin, the same pigment that colors human skin, and it appears to help them harness radiation as an energy source, much like plants use sunlight. This process, called radiosynthesis, is still not fully understood, but it suggests fungi are even more versatile than we imagined. In one of the most hostile environments humans have ever created, fungi not only survived, but flourished, turning deadly radiation into fuel. They remind us that life is persistent, adaptive, and full of surprises. Yeasts are single-celled fungi essential to bread and beer. Not all fungi form sprawling networks or large mushrooms. Some exist as single cells, floating in liquids or coating surfaces. These are yeasts, and they have shaped human civilization in profound ways. When you bake bread, yeast consumes sugars in the dough and releases carbon dioxide, causing the bread to rise. When you brew beer or ferment wine, yeast converts sugars into alcohol. This process, fermentation, has been used by humans for thousands of years, long before we understood what yeast actually was. Ancient Egyptians brewed beer, medieval monks perfected winemaking, and every culture developed its own fermented foods. All relied on these tiny fungi. Even today, industrial yeast is essential to baking, brewing, and even biofuel production. Yeasts are quiet workers, invisible to the naked eye, yet their impact on human culture is immeasurable. Without them, our diets, our celebrations, and our history would look entirely different. Penicillin, the first antibiotic, comes from a fungus. In 1928, a Scottish scientist named Alexander Fleming returned to his laboratory after a vacation and noticed something strange. A petri dish containing bacteria had been contaminated by mold, and around the mold, the bacteria had died. The mold was Penicillium notatum, a common fungus, and it was producing a substance that killed bacteria. Fleming called this substance penicillin, and it would go on to become the world's first widely used antibiotic. Before penicillin, even minor infections could be deadly. A cut, a scrape, or a surgical procedure carried significant risk. Penicillin changed that, saving countless lives during World War II and in the decades since. It launched the age of antibiotics, transforming medicine. This life-saving drug came not from a laboratory invention, but from a humble fungus, a reminder that nature often holds solutions to our greatest challenges, if only we take the time to look. Fungi produce many other medicines, from immunosuppressants to cholesterol drugs. Penicillin was just the beginning. Over the decades, researchers have discovered numerous other medically important compounds produced by fungi. Cyclosporin, derived from a fungus found in Norwegian soil, revolutionized organ transplantation by suppressing the immune system and preventing rejection. Statins, used by millions to lower cholesterol and prevent heart disease, were first isolated from fungi. Other fungal compounds show promise in fighting cancer, viral infections, and inflammatory diseases. Fungi's chemical diversity is staggering. Living in competitive environments, they produce compounds to defend themselves, communicate, or attack rivals. These same compounds often have effects on human biology, making fungi a treasure trove for pharmaceutical research. As we explore more ecosystems and study more species, we continue to find new fungal compounds with potential medical applications. The quiet work of fungi decomposing a log in a forest might one day lead to a cure for a disease that has plagued humanity for generations. Truffles are rare fungi that grow underground and can be worth thousands. Among the most prized culinary ingredients in the world are truffles, fungi that grow entirely underground in association with tree roots. Unlike mushrooms that emerge into the open air, truffles remain hidden, producing their spores below the soil. They rely on animals, particularly wild pigs and specially trained dogs, to dig them up and spread their spores. Their aroma is powerful and distinctive, a complex scent that humans have prized for centuries. Black truffles, white truffles, and other varieties can sell for thousands of dollars per pound, making them one of the most expensive foods on Earth. Truffle hunters guard their secret locations, venturing into forests with trained animals to sniff out these hidden treasures. The rarity, the difficulty of cultivation, and the intense flavor make truffles legendary. Yet they are simply fungi, doing what fungi do, forming partnerships with trees, living quietly underground, waiting to be discovered. Dogs and pigs can smell truffles buried deep beneath the soil. Truffles produce a scent that mimics certain animal pheromones, which is why pigs are naturally attracted to them. For centuries, truffle hunters used pigs to locate these buried fungi, though the pigs often wanted to eat the truffles themselves, making retrieval tricky. Today, dogs are more commonly trained for truffle hunting. They can be taught to detect the scent without devouring the prize, and they are easier to manage in the field. A skilled truffle dog can locate fungi buried a foot or more beneath the surface, sniffing out the faint aroma that escapes through the soil. The bond between hunter and dog is essential, built on trust and communication. Together, they wander through forests, searching for hidden wealth. It is a profession that has remained largely unchanged for generations, a quiet partnership between human, animal, and fungus, all connected by scent and soil. Mushrooms can appear overnight after rain, seemingly from nowhere. One of the most enchanting sights in nature is the sudden appearance of mushrooms after a rainstorm. You walk through a familiar patch of woods, and the ground is bare. The next morning, after a night of rain, mushrooms have sprouted everywhere, as if conjured by magic. This rapid growth is possible because the mycelium has been growing underground for weeks, months, or even years, building up energy and resources. When conditions are right, when moisture and temperature align, the mycelium rapidly pushes up fruiting bodies. The mushroom itself grows quickly, sometimes in just a few hours, expanding as water fills its cells. By the time you see it, the hard work has already been done beneath the surface. The mushroom is simply the final flourish, a brief moment of visibility in a life spent mostly hidden. Within days, it will release its spores and decay, returning to the earth, while the mycelium continues its patient work below. Some mushrooms can push through asphalt and concrete. Fungi may seem delicate, but they possess surprising strength. The pressure exerted by a growing mushroom can be immense, enough to crack asphalt, lift paving stones, or push through compacted soil. This force comes from the rapid uptake of water, which inflates the cells of the mushroom, creating hydraulic pressure. Imagine thousands of tiny cells, filling with water simultaneously, expanding with relentless force. Concrete may seem impenetrable, but it has cracks and weak points, and a determined mushroom can exploit them. Over time, fungi contribute to the breakdown of human structures, reclaiming urban spaces slowly but surely. Abandoned buildings, forgotten roads, and neglected sidewalks all become substrates for fungal growth. The image of a small mushroom splitting concrete is a powerful reminder that nature is patient and persistent. What humans build, fungi can slowly dismantle, returning it to the earth from which it came. Fairy rings are natural circles of mushrooms formed by expanding mycelium. In meadows and lawns, you might notice mushrooms growing in near-perfect circles, sometimes stretching many feet across. These are called fairy rings, and they have inspired folklore for centuries. In some cultures, they were thought to mark places where fairies danced. In others, they were seen as portals to other worlds, or omens of good or bad fortune. The truth is more subtle but no less fascinating. A fairy ring forms when mycelium grows outward from a central point in all directions, forming a circular mat underground. As the mycelium expands, it depletes nutrients in the soil at the center, and only the outer edge remains active. Each year, mushrooms fruit along this leading edge, creating a ring that grows larger over time. Some fairy rings are hundreds of years old, expanding slowly year after year, marking the invisible growth of a hidden organism. They are nature's own geometry, drawn in mushrooms and mystery. Some fairy rings can be centuries old, expanding outward year by year. The oldest known fairy rings are enormous, stretching dozens of meters across, and are estimated to be over 700 years old. Each year, the mycelium extends a little farther, and the ring of mushrooms grows slightly larger. To stand inside an ancient fairy ring is to occupy a space that has been shaped by a single organism for longer than most nations have existed. These rings grow slowly, sometimes only a few inches per year, but their persistence is remarkable. They survive droughts, fires, and the passage of countless seasons. The mycelium beneath remains active, constantly extending, feeding, and fruiting. In a world where so much changes quickly, fairy rings offer a different sense of time. They remind us that some processes unfold over centuries, patient and unhurried, visible only to those who pay attention across generations. Fungi can form partnerships with algae to create lichens. In some of nature's most remarkable collaborations, fungi and algae, or cyanobacteria, come together to form lichens. These organisms appear as crusty, leafy, or branching growths on rocks, trees, and soil. The fungus provides structure and protection, while the algae or cyanobacteria photosynthesize, producing food for both. This partnership allows lichens to survive in places where neither organism could live alone. They colonize bare rock in deserts, cling to trees in rainforests, and thrive in the frozen Arctic. Lichens are incredibly slow-growing, some expanding only a millimeter per year, but they are also incredibly long-lived. Some Antarctic lichens are thought to be thousands of years old. They are pioneers, often the first life to colonize barren landscapes, slowly breaking down rock and creating soil for other organisms. Lichens remind us that cooperation can achieve what individuals cannot, that partnership is a powerful strategy for survival. Lichens can survive in space, enduring vacuum and radiation. Scientists have conducted experiments exposing lichens to the harsh conditions of space, and the results are astonishing. Lichens survived exposure to vacuum, extreme temperature fluctuations, and intense radiation for extended periods. When returned to Earth, many resumed normal growth as if nothing had happened. This resilience suggests that life, or at least certain forms of it, might be able to survive interplanetary travel. Could lichens, or organisms like them, hitch rides on meteorites, spreading from planet to planet? The idea, called panspermia, remains speculative, but lichens' toughness makes it seem a little less far-fetched. These humble crusts clinging to rocks are among the hardiest life forms we know, capable of enduring conditions that would destroy most living things. They blur the line between earthbound life and the possibility of life beyond, quiet survivors with the strength to endure the cosmos itself. Lichens grow so slowly, they're used to date ancient rock surfaces. Because lichens grow at such predictable, slow rates, scientists use them as living clocks. By measuring the size of lichen colonies on rocks, researchers can estimate how long those surfaces have been exposed. This technique, called lichenometry, has been used to date glacial moraines, rockfalls, and ancient stone structures. In some cases, lichen dating has provided valuable information where other dating methods fail. Of course, accuracy depends on knowing the growth rate of the specific lichen species in that climate, but when done carefully, it works remarkably well. Imagine a lichen colony the size of your hand, growing on a boulder. That colony might be hundreds of years old, a living record of time passing, growing so slowly you could watch it your entire life and barely notice a change. Lichens teach us patience, and they offer science, a tool for understanding the age of landscapes, all while quietly clinging to stone. Mushrooms come in an astonishing variety of colors and shapes. If you think mushrooms are all brown or white, a walk through the woods will change your mind. Fungi produce fruiting bodies in nearly every color imaginable. Bright reds, deep purples, electric blues, glowing oranges, and even vivid greens. Some mushrooms look like tiny umbrellas, others like coral, fans, shelves, cups, or even lattices. The diversity is staggering. Each shape and color serves a purpose, whether attracting animals to spread spores, deterring predators, or simply reflecting the chemicals the fungus produces. The bleeding tooth fungus oozes red droplets that look like blood. The blue milk-cap secretes a bright blue latex. The fly agaric, with its iconic red cap dotted with white, looks like it belongs in a fairy tale. This variety makes mushroom hunting endlessly fascinating. Every walk can yield a new discovery, a new color, a new form. The kingdom of fungi is an artist's palette, painting the forest floor with shapes and hues beyond imagination. The fly agaric mushroom is iconic in folklore and fairy tales. With its bright red cap speckled with white spots, the fly agaric is one of the most recognizable mushrooms in the world. It appears in countless fairy tales, illustrations, and stories, often associated with magic, fairies, or enchantment. The mushroom is also toxic, containing compounds that cause hallucinations and other symptoms if ingested. Historically, some cultures used it in shamanic rituals for its psychoactive effects, though this was dangerous and unpredictable. The name fly agaric comes from its traditional use as an insecticide. Pieces of the mushroom were placed in milk to attract and kill flies. Despite its dangers, the fly agaric holds a special place in human imagination. It is the mushroom of storybooks, the toadstool where fairies might sit. Its vivid appearance captures something primal in us, a sense that the forest holds secrets, that some things are beautiful and dangerous in equal measure. Some mushrooms are deadly poisonous, even in tiny amounts. Not all mushrooms are safe. Some are among the most toxic substances known to nature. The death-cap mushroom, Amanita phalloides, is responsible for the majority of fatal mushroom poisonings worldwide. It looks deceptively ordinary, with a greenish or pale cap, and it can be mistaken for edible varieties. Just a single mushroom can contain enough toxins to kill an adult. The poisons attack the liver and kidneys, and symptoms often don't appear until it's too late for effective treatment. Other deadly mushrooms include the destroying angel and certain species of Gallerina. Eating wild mushrooms without expert identification is incredibly dangerous. Every year, people are poisoned, sometimes fatally, because they misidentified a mushroom. The lesson is clear. The beauty and bounty of fungi come with risk. Respect for these organisms includes understanding that some are best admired from a distance. Their toxins, a reminder that nature is not always benign. The toxins in death caps survive cooking and drying. One of the frightening aspects of deadly mushrooms like the death cap is that their toxins are remarkably stable. You cannot destroy them by cooking, boiling, freezing, or drying. The heat that makes food safe does nothing to neutralize these compounds. This means that even a carefully prepared dish containing death caps remains lethal. The toxins are absorbed quickly by the body, and once symptoms appear, often days after ingestion, the damage is already done. Liver transplants are sometimes the only option for survival. Historically, poisonings have occurred when foragers mistook death caps for edible species, like puffballs or straw mushrooms. The tragic consequences remind us that knowledge and caution are essential when dealing with wild fungi. The same kingdom that gives us delicious edibles and life-saving medicines also harbors silent killers, and the difference between the two is not always obvious to the untrained eye. Some mushrooms are prized edibles, treasured by chefs worldwide. While some fungi are dangerous, others are culinary treasures. Morels, chanterelles, porcini, and matsutake are just a few of the mushrooms prized by chefs and food lovers. These wild mushrooms have complex flavors that farmed varieties often lack, with earthy, nutty, or even fruity notes. Morels, with their honeycomb caps, appear in spring and are hunted eagerly by foragers. Chanterelles, golden and trumpet-shaped, fruit in summer and fall, often in the same locations year after year. Porcini, thick-stemmed and meaty, are beloved in European cuisine. Matsutake, aromatic and rare, command high prices in Japan. Foraging for these mushrooms connects people to the land, requiring knowledge of seasons, weather, and specific habitats. It is a practice that combines patience, skill, and a bit of luck. Each successful find feels like a gift from the forest, a reminder that some of the finest flavors come not from fields or farms, but from the wild, quiet places where fungi grow. Mushroom foraging requires expertise and careful identification. The appeal of finding wild mushrooms is strong, but the risks are real. Foraging requires careful study, often years of learning to identify species correctly. Many edible mushrooms have toxic lookalikes, and a single mistake can be fatal. Experts recommend never eating a wild mushroom unless you are absolutely certain of its identity, and even then, trying only a small amount the first time to check for individual sensitivities. Field guides, local mycological societies, and experienced foragers are invaluable resources. Some people spend decades learning their local fungi, building a mental catalogue of species, habitats, and seasons. Foraging is not just about collecting food. It is about observation, respect for nature, and understanding the ecosystems fungi inhabit. It is a slow practice, one that rewards patience and caution. For those who take the time to learn, foraging offers not just edible rewards, but a deeper connection to the natural world. Fungi decompose dead matter, returning nutrients to the soil. Imagine a forest without fungi. Dead trees would accumulate, layer upon layer, never rotting. Fallen leaves would pile up endlessly. Nutrients would remain locked in dead organic matter, unavailable to living plants. The ecosystem would collapse. Fungi prevent this by breaking down dead material, releasing nutrients back into the soil where plants can use them. Fungi secrete enzymes that dissolve lignin, cellulose, and other tough compounds that most organisms cannot digest. They are essential recyclers, the cleanup crew of the natural world. Without them, life as we know it could not exist. Every rotting log, every decomposing leaf, every piece of organic debris is being processed by fungi, transformed from death into the building blocks of new life. When you walk through a forest and breathe in the earthy scent of decay, you are smelling the work of fungi, the quiet transformation that keeps the cycle of life turning. Some fungi specialize in breaking down specific materials, like lignin. Lignin is one of the toughest natural substances, a complex polymer that gives wood its strength and rigidity. Most organisms cannot break it down, but some fungi specialize in it. White rot fungi, for example, are among the few organisms that can efficiently decompose lignin, leaving behind pale, crumbly wood. Brown rot fungi break down cellulose, but leave lignin relatively intact, resulting in brown, fragmented wood. These specialists play crucial roles in forest ecosystems, recycling the vast amounts of woody material that accumulate over time. Their ability to break down such resilient compounds has attracted scientific interest. Researchers are studying these fungi for potential applications in biofuels, waste treatment, and even the breakdown of pollutants. The same enzymes that rot a tree trunk might one day help us process agricultural waste or clean up contaminated sites. Nature's solutions are often elegant and efficient, refined over millions of years. Fungi create the rich, earthy scent of a forest floor. The smell of a forest after rain is one of nature's most evocative scents, earthy, rich, and grounding. Much of that aroma comes from fungi and the compounds they release as they grow and decompose organic matter. One particular compound, geosmin, is produced by fungi and certain bacteria, and it is responsible for that quintessential petrichor smell, the scent of earth after rain. Humans are remarkably sensitive to geosmin, able to detect it in incredibly tiny concentrations. This scent is deeply tied to our experience of nature, triggering memories and emotions. It tells us the soil is alive, that decomposition and renewal are happening beneath our feet. When you breathe in the smell of the forest, you are inhaling the chemical signatures of countless fungi at work, breaking down, building up, cycling nutrients, and transforming the world in ways invisible but profoundly present. Mushrooms are low in calories but rich in nutrients. For those who enjoy eating mushrooms, there is good news. They are nutritious, low in calories, and contain compounds beneficial to health. Mushrooms provide protein, fiber, vitamins like B and D, and minerals such as selenium and potassium. Some varieties, especially when exposed to sunlight, are excellent sources of vitamin D, rare in plant-based foods. They also contain antioxidants and polysaccharides that may support immune function. While they should not be relied on as a sole source of nutrition, mushrooms are a valuable addition to a balanced diet. Cultures around the world have recognized this for millennia, incorporating mushrooms into traditional dishes, not just for flavor, but for sustenance. Whether sautéed, dried, or simmered in soups, mushrooms bring umami depth and nutritional value to meals. They remind us that fungi are not just ecological players, but also sources of nourishment, quietly contributing to human health and cuisine. Some cultures have revered mushrooms for thousands of years. In many cultures, mushrooms hold a place of honor. In China and Japan, certain fungi, like reishi and shiitake, have been used in traditional medicine for centuries, prized for their purported health benefits. In Mesoamerica, some indigenous groups used psychoactive mushrooms in religious ceremonies, believing they provided spiritual insights. European folklore is filled with references to mushrooms, often treating them with a mix of fascination and fear. In Russia, mushroom foraging is a beloved national pastime, with families venturing into forests each season to gather wild varieties. These cultural traditions reflect a deep relationship between humans and fungi, one that goes beyond simple utility. Mushrooms have been teachers, healers, symbols, and sacraments. They connect us to the earth, to mystery, and to practices passed down through generations. In honoring fungi, these cultures acknowledge something we often forget in modern life: that we are part of a living world, and that other organisms have much to offer if we approach them with respect. Psychoactive mushrooms have been used in spiritual practices. Certain mushrooms contain compounds like psilocybin that profoundly alter human consciousness. For thousands of years, indigenous cultures in Central and South America have used these mushrooms in religious and healing ceremonies. Participants report visions, a sense of connection to the universe, and insights into their own lives. These experiences are not recreational, but sacred, guided by tradition and ritual. In recent years, modern science has begun studying psilocybin for its potential therapeutic benefits. Research suggests it may help treat depression, anxiety, PTSD, and addiction, often with lasting effects from just a few sessions. The mechanisms are still being explored, but it appears psilocybin allows the brain to form new connections, breaking rigid patterns of thought. These studies mark a return to taking these fungi seriously, not as mere intoxicants, but as tools for healing and understanding. The mushrooms that once guided spiritual journeys may yet guide us toward new approaches to mental health. Modern research is exploring psilocybin for treating depression and PTSD. Clinical trials in recent years have shown promising results. Patients with treatment-resistant depression, those who have tried many medications without success, report significant improvements after psilocybin-assisted therapy. The experience is often described as deeply meaningful, sometimes life-changing. Unlike traditional antidepressants, which must be taken daily, psilocybin seems to have lasting effects after just 1 or 2 sessions, though in a controlled, therapeutic setting with professional guidance. Similar results have been seen with PTSD and end-of-life anxiety in terminal patients. The substance does not simply numb emotions, but appears to help people process trauma and shift perspective. Researchers emphasize that this is not about casual use. The therapeutic context, preparation, and integration are crucial, yet the potential is exciting. A humble mushroom, used for millennia in spiritual contexts, may offer relief where modern medicine has struggled. It is a reminder that ancient wisdom and cutting-edge science can sometimes converge, each illuminating the other. Cordyceps fungi infect insects and alter their behavior. In the forests of Southeast Asia and other regions, a macabre drama unfolds. Cordyceps fungi infect insects, particularly ants, and take control of their behavior. The fungus grows inside the insect's body, consuming it from within, and then manipulates the insect to climb to a high point, often a plant stem or leaf. There, the insect dies, and the fungus erupts from its body, producing a fruiting body that releases spores to infect other insects. This parasitic relationship is both horrifying and fascinating. The fungus effectively turns its host into a zombie, hijacking its nervous system to serve the fungus's reproductive needs. Dozens of cordyceps species target different insect species, each highly specialized. Watching time-lapse footage of this process is unsettling, a reminder that nature's strategies for survival can be as ruthless as they are ingenious. These fungi blur the line between life and death, between individual and organism, revealing a world far stranger than we usually imagine. The zombie ant fungus has inspired horror and science fiction. The image of an organism taking control of another's body and mind is deeply unsettling, and cordyceps has inspired countless works of horror and science fiction. Video games like The Last of Us depict a world where a mutated cordyceps infects humans, turning them into mindless, fungus-controlled creatures. While purely fictional, the scenario resonates because it is rooted in something real. Cordyceps does control insects, and while it cannot infect humans, the concept taps into primal fears of losing autonomy, of being consumed from within. In reality, cordyceps is just a fungus trying to survive, using the strategies evolution has given it. But its existence reminds us that the natural world contains horrors as well as wonders, that life's strategies can be beautiful, brutal, or both. These fungi have become symbols of nature's dark side, yet they also invite us to marvel at the complexity and strangeness of life on Earth. Some cordyceps species are harvested for traditional medicine. Not all cordyceps are sinister parasites. Some species, particularly Cordyceps sinensis, have been used in traditional Chinese medicine for centuries. This species parasitizes caterpillars in the high mountains of Tibet and Nepal, producing a distinctive fruiting body that emerges from the mummified host. The combination of caterpillar and fungus is harvested and sold at extraordinary prices, sometimes more expensive than gold. It is believed to boost energy, support the immune system, and promote longevity. Scientific studies have explored these claims with mixed results, but the market for cordyceps remains strong. Wild populations have been over-harvested, leading to concerns about sustainability. Now, some species are cultivated commercially, on grain or in labs, providing an alternative source. Whether cordyceps truly delivers the health benefits attributed to it remains an area of ongoing research, but its place in traditional medicine reflects a long history of humans turning to fungi for healing and vitality. Slime molds are often mistaken for fungi, but are different organisms. Slime molds are among the strangest organisms you might encounter in a forest, and for a long time, they were classified as fungi. They ooze slowly across logs and leaf litter, looking like blobs of goo, often brightly colored in yellow, orange, or pink. But slime molds are not fungi. They are protists, more closely related to amoebas than to mushrooms. During part of their life cycle, they exist as single-celled organisms, but under certain conditions, thousands of these cells merge into a single giant cell called a plasmodium, which can move, sense its environment, and even solve simple problems. Despite lacking a brain or nervous system, slime molds can navigate mazes, find the shortest path between food sources, and remember previous encounters. Scientists study them as models of simple intelligence, showing that problem-solving and decision-making do not require neurons. Slime molds remind us that life is diverse, beyond our everyday categories, and intelligence can emerge in the most unexpected forms. Slime molds can solve mazes and optimize networks. In laboratory experiments, researchers have presented slime molds with mazes, placing food at the entrance and exit. The slime mold explores the maze, extending tendrils into every path. Over time, it retracts from dead ends and reinforces the shortest route between the food sources. The result is a solution to the maze, achieved without thought or planning. In another experiment, scientists placed oat flakes, a slime mold favorite, at locations corresponding to cities around Tokyo, and placed the slime mold in the center. The organism extended tendrils to connect all the food sources, creating a network strikingly similar to the Tokyo rail system, an efficient design developed over decades by engineers. The slime mold achieved it in hours. These experiments reveal that optimization and problem-solving can arise from simple biological rules. The slime mold is not thinking, but it is behaving intelligently. adapting to its environment in ways that mimic intelligent design. It is a humbling reminder that nature often arrives at elegant solutions long before humans do. Fungi play a role in creating soil from bare rock. When you think of soil, you might imagine rich, dark earth, but all soil begins as rock. Fungi are among the first organisms to colonize bare rock, along with lichens and certain bacteria. Their hyphae penetrate tiny cracks, secreting acids that slowly dissolve minerals. This process, called weathering, breaks down rock into smaller particles. Over centuries and millennia, this contributes to the formation of soil. Dead fungal material adds organic matter, and as other organisms move in, the soil becomes richer and more complex. Without fungi, the transformation of rock into soil would be vastly slower. They are pioneers, the first to arrive in barren places, patiently creating conditions where other life can follow. This role places fungi at the very foundation of terrestrial ecosystems, literally building the ground on which forests, grasslands, and farms depend. Every handful of soil owes part of its existence to the slow, persistent work of fungi. Some fungi can clean up oil spills and toxic waste. The same enzymes that allow fungi to decompose wood also enable some species to break down petroleum products and other pollutants. Oyster mushrooms, for example, can digest hydrocarbons in oil, breaking them down into simpler, less harmful compounds. This process, called mycoremediation, is being studied as a tool for environmental cleanup. In contaminated sites, fungi can be introduced to the soil or spread on oil-soaked surfaces. Over time, they reduce the concentration of toxins, helping to restore the area. Mycoremediation is not a quick fix. It takes time, and it works best in combination with other methods. But it is a low-cost, natural approach that harnesses fungi's decomposing power. As we face increasing environmental challenges, fungi may offer solutions we have overlooked. The same organisms that rot a log can also heal poisoned land, quietly breaking down what harms us and returning the earth to health. Mushroom leather and packaging are sustainable alternatives. In the search for sustainable materials, fungi are offering surprising solutions. Mycelium, the thread-like network of fungi, can be grown into specific shapes and forms, creating materials that resemble leather, foam, or even building blocks. Companies are developing mycelium-based leather alternatives that look and feel similar to animal leather, but are grown in weeks rather than requiring animal hides. Mycelium packaging is another innovation, providing a biodegradable alternative to styrofoam. Agricultural waste, like sawdust or corn stalks, is mixed with mycelium, which binds it together as it grows. The resulting material is lightweight, compostable, and can be molded into protective packaging. When disposed of, it breaks down naturally, feeding back into the soil. These innovations are still in their early stages, but they represent a shift toward using biology, rather than chemistry, to produce materials. Fungi, the ancient decomposers, are now helping us build a more sustainable future. Mycelium can be used to grow building materials. Beyond leather and packaging, mycelium is being explored as an actual building material. Researchers have grown mycelium into bricks, panels, and structural components. These materials are surprisingly strong, lightweight, fire-resistant, and, most importantly, biodegradable. Imagine a building that, at the end of its life, could be composted rather than demolished and sent to a landfill. Mycelium construction is still experimental, but prototypes have been built, including pavilions, furniture, and even small structures. The process is simple. Agricultural waste is inoculated with mycelium, packed into molds, and allowed to grow. Within days or weeks, the mycelium binds the material together, creating a solid form. The growth is then stopped, usually with heat, to stabilize the structure. While mycelium buildings are not yet mainstream, they represent a vision of architecture that works with nature rather than against it, where growth and decay are part of the design rather than problems to be avoided. Fungi helped ancient civilizations preserve food through fermentation. Long before refrigeration, humans needed ways to preserve food. Fermentation, driven by fungi and bacteria, provided an answer. Yeasts ferment sugars in grapes to create wine, in grains to produce beer, and in dough to make bread rise. Molds transform milk into cheese, each variety with its own fungal cultures. In East Asia, koji, a fungus cultured on rice or soybeans, is essential to making soy sauce, miso, and sake. These fermented foods are not just preserved, they are transformed, gaining new flavors, textures, and nutritional qualities. Fermentation was discovered independently by cultures worldwide, each developing unique traditions. It represents an ancient partnership between humans and fungi, one that continues today. Every sip of wine, every bite of cheese, every slice of sourdough bread is a product of this collaboration. Fungi turn simple ingredients into something complex and enduring, preserving not just food, but culture and tradition. Cheese rinds are often grown using specific fungi. Many cheeses develop distinctive rinds, and fungi are responsible. Soft cheeses like brie and camembert are coated with Penicillium candidum, which creates their white, velvety rinds. Blue cheeses like Roquefort and Gorgonzola are inoculated with Penicillium roqueforti, which grows throughout the cheese, creating blue-green veins and sharp, tangy flavors. Hard cheeses may develop natural rinds from wild yeasts and molds in the aging environment. Each fungus contributes unique flavors, textures, and aromas. Cheesemakers carefully control these cultures, choosing specific strains to achieve desired results. The rind is not just decoration. It protects the cheese and influences the development of flavor as the cheese ages. Some rinds are edible, others are not, but all are evidence of fungi's role in transforming milk into something far more complex. The next time you enjoy a wedge of cheese, consider the invisible work of fungi, shaping flavor molecule by molecule. Soy sauce and miso rely on fungal fermentation. In many Asian cuisines, fermented soy products are essential. Soy sauce, miso, and tempeh all depend on fungi, particularly species of Aspergillus. To make soy sauce, soybeans and wheat are inoculated with Aspergillus oryzae, also known as koji. The fungus breaks down proteins and starches, releasing amino acids and sugars. The mixture is then fermented with salt water, sometimes for months or years, developing the rich, umami flavor characteristic of soy sauce. Miso follows a similar process, resulting in a thick paste used in soups, marinades, and dressings. Tempeh, a traditional Indonesian food, uses a different fungus, Rhizopus, which binds cooked soybeans into a firm, sliceable cake. These products are not just flavorful but nutritious, with proteins more digestible than in raw soybeans. Fermentation through fungi is a form of culinary alchemy, turning humble ingredients into staples that have fed billions of people for centuries. Kombucha involves yeast and bacteria, including fungal species. Kombucha, a tangy, fermented tea, has gained popularity in recent years, but it has been consumed for centuries, particularly in Asia. It is made by fermenting sweetened tea with a symbiotic culture of bacteria and yeast, often called a SCOBY. While the culture includes bacteria, yeasts, which are fungi, play a crucial role. These yeasts consume sugars, producing alcohol and carbon dioxide, while bacteria convert the alcohol into acetic and other acids, giving kombucha its characteristic tartness. The result is a slightly fizzy, sour beverage that enthusiasts claim offers health benefits, though scientific evidence is still being gathered. The SCOBY itself is a fascinating organism, or rather, a community of organisms, working together in a thick, rubbery layer. Homebrewers can maintain a SCOBY for years, using it to ferment batch after batch. Kombucha is a reminder that fermentation is not a single process, but a collaboration, a tiny ecosystem in a jar. Fungi produce enzymes used in detergents and textiles. The enzymes fungi produce are not just useful for decomposition. Industry has harnessed them for various purposes. Cellulase enzymes break down cellulose, used in textile manufacturing to soften fabrics and create the worn look of stonewashed jeans. Protease enzymes, which break down proteins, are added to laundry detergents to remove stains. Amylase enzymes, which break down starches, are used in baking and brewing. Many of these enzymes are derived from fungi, which produce them naturally as part of their feeding process. Industrial production involves growing fungi in large fermentation tanks, harvesting the enzymes and purifying them for use. This approach is often more sustainable than chemical processes, using biological catalysts that work efficiently at low temperatures. Fungi, the great decomposers, have become industrial partners, their enzymes quietly working in products we use every day, from our clothes to our food. Some fungi can produce biofuels from plant waste. As the world seeks alternatives to fossil fuels, fungi are offering potential solutions. Certain fungi can break down cellulose and lignin in plant waste, like corn stalks, wood chips, or grasses, converting it into simple sugars. These sugars can then be fermented into ethanol, a biofuel. This process could turn agricultural waste, which is abundant and often burned or discarded, into energy. The challenge is doing it efficiently and economically. Researchers are studying fungi that decompose plant material quickly and completely, screening wild species and engineering strains with enhanced abilities. If successful, fungal biofuel production could reduce reliance on fossil fuels, lower greenhouse gas emissions, and make use of materials that would otherwise go to waste. It is another example of fungi's versatility, their ability to break down the toughest materials and transform them into something useful, whether for nature's cycles or human needs. Fungi communicate through chemical signals in the soil. Fungi may seem simple, but they are far from passive. They sense their environment, responding to chemical signals from plants, other fungi, and microorganisms. When a plant's roots detect a nutrient deficiency, they release chemical signals into the soil. Mycorrhizal fungi respond, extending hyphae toward the roots and forming partnerships. Fungi also release their own signals, marking territory, attracting partners, or deterring competitors. These chemical conversations happen constantly beneath our feet, invisible and complex. Some scientists describe mycelial networks as information highways, transmitting not just nutrients, but signals that coordinate the growth and behavior of entire ecosystems. While we are only beginning to understand this fungal communication, it suggests a level of sophistication we did not expect. Fungi are not just growing randomly. They are responding, adapting, and interacting in a dynamic underground world. The Wood Wide Web allows trees to share nutrients through fungi. One of the most remarkable discoveries in recent ecology is that trees are not isolated individuals, but members of a networked community. Mycorrhizal fungi connect trees, allowing them to share carbon, nitrogen, and other nutrients. A large, well-established tree, with access to ample sunlight, can send excess carbon through the network to smaller, shaded trees struggling to photosynthesize. In return, those smaller trees might share other resources when conditions change. This system has been called the wood wide web, a term that captures the sense of a living internet beneath the forest floor. It challenges the old view of nature as purely competitive, showing instead that cooperation and mutual support are fundamental to forest health. The fungi benefit too, receiving sugars from the trees, while extending the tree's reach into the soil. It is a three-way partnership: trees, fungi, and soil, each depending on the others. The forest is not a collection of individuals, but a superorganism, bound together by fungal threads. Mother trees support their young through fungal networks. Research by scientists like Suzanne Simard has shown that older, larger trees, often called mother trees, play a crucial role in forest health. These trees are hubs in the mycorrhizal network, connected to many other trees, especially their own offspring. Mother trees send carbon and nutrients to their seedlings through the fungal network, helping them survive in the shaded understory where light is scarce. This support increases the seedling's chances of survival. When a mother tree is dying, it may even increase the transfer of resources, as if passing on an inheritance. This behavior suggests a level of cooperation and care that was not previously attributed to trees and fungi. It reframes forests as communities with relationships, memory, and communication. The next time you walk through a forest, consider that the trees around you may be sharing, supporting, and nurturing each other through an invisible network, a web of life that connects every root and every thread of mycelium. Fungi can recognize and respond to the presence of other organisms. Fungi are not solitary. They grow in environments teeming with other organisms, and they have evolved to sense and respond to their neighbors. When a fungus encounters another fungus, it can recognize whether it is kin, ally, or competitor. If it is kin, they may fuse, sharing resources and cooperating. If it is a competitor, they may battle, releasing chemical weapons or growing barriers to exclude each other. Fungi also sense plants, bacteria, and even predators like nematodes. Some fungi, when threatened by nematodes, develop specialized traps, loops or nets that capture and immobilize the tiny worms. The fungus then penetrates the nematode and digests it, turning predator into prey. These responses show that fungi are not passive. They are dynamic, reactive organisms capable of complex behaviors. They perceive their world through chemistry, responding to threats and opportunities, with strategies honed over millions of years. Some fungi form traps to catch and digest tiny worms. In the soil, microscopic dramas unfold. Certain fungi have evolved to hunt. When nematodes, tiny roundworms, are abundant, some fungi develop specialized structures to catch them. These traps can be sticky knobs that worms adhere to, or constricting loops that tighten like a noose when a worm passes through. Once caught, the fungus penetrates the nematode's body with hyphae, secreting enzymes that dissolve the worm from the inside. The fungus absorbs the nutrients, gaining nitrogen and other resources scarce in the soil. These carnivorous fungi are reminders that predation takes many forms. Not just teeth and claws, but traps made of living cells set with patience in the darkness of the soil. The nematodes, usually hunters themselves, become prey, victims of a fungal strategy that is both ingenious and ruthless. It is a world of eat or be eaten, even among organisms too small to see without a microscope. Fungi can detect light and orient their fruiting bodies. Though fungi do not photosynthesize, many can sense light. This ability helps them orient their fruiting bodies, for optimal spore dispersal. A mushroom growing beneath a log will often direct its cap toward the light, ensuring spores fall in open air where wind can carry them. Some fungi exhibit phototropism, bending toward light sources as they grow. Others use light as a cue to begin fruiting, timing their reproduction to match favorable conditions. This sensitivity shows that fungi, despite living mostly underground, are aware of the world above. They respond to day and night, to seasons, to the opening of the canopy. This awareness is not conscious, but it is effective, allowing fungi to maximize their reproductive success. In the dim light of the forest floor, fungi wait and watch, ready to send their spores into the world when the moment is right. Spores can survive extreme conditions and remain viable for years. Fungal spores are among nature's most resilient structures. Encased in tough walls, they can survive freezing, drought, heat, and even radiation. Some spores remain viable for decades, waiting patiently for conditions to improve. When moisture, temperature, and other factors align, the spore germinates, sending out hyphae to begin a new mycelium. This resilience allows fungi to colonize harsh environments and survive catastrophes that wipe out other organisms. Spores can travel vast distances, carried by wind, water, or animals, spreading fungi across continents. They are found in the highest reaches of the atmosphere and in the deepest ocean sediments. Their durability makes fungi nearly ubiquitous, present almost everywhere life exists. A single mushroom can release billions of spores, most of which will never find suitable conditions. But a few will, and that is enough. Spores are the seeds of the fungal world, tiny, persistent, and remarkably tough. A single mushroom can release billions of spores in its lifetime. The reproductive capacity of fungi is staggering. A large mushroom can produce billions, even trillions, of spores. These microscopic particles are released from the underside of the cap, from gills, pores, or other structures. Once released, spores drift on air currents, traveling miles or even continents. Most will land in unsuitable places and perish. But with such astronomical numbers, even a tiny success rate is enough. A few spores will land where conditions are right, germinate, and begin new mycelia. This strategy, producing vast numbers of offspring with minimal investment in each, is common in nature. It ensures that fungi can colonize new territories, recover from disturbances, and persist through changing conditions. When you see a mushroom releasing its spores, you are witnessing one of nature's grandest lotteries, billions of chances cast into the wind, each one a potential new beginning. Spores are found everywhere, from the air to deep ocean sediments. Fungal spores are part of the air we breathe. Samples of atmosphere collected by aircraft reveal spores floating miles above the surface, carried by winds, sometimes traveling across oceans. Spores have been found in the stratosphere, in desert sands, in Arctic ice, and in the deepest ocean trenches. This ubiquity means fungi can potentially colonize almost any environment where conditions allow, even if only briefly. Spores landing in inhospitable places may lie dormant for years, waiting for conditions to change. This dispersal ability is one reason fungi are so successful. They are everywhere, invisible passengers on the wind, settling quietly on surfaces, waiting for the right moment to grow. Every breath you take likely contains fungal spores, harmless travelers in the air, reminding us that we are never truly separate from the living world. We are immersed in it, surrounded by life in forms we rarely notice. Fungi reproduce both sexually and asexually. Fungi have diverse reproductive strategies, using both sexual and asexual reproduction depending on circumstances. Asexual reproduction is simpler and faster. A fragment of mycelium breaks off and grows into a new organism, or specialized asexual spores are produced and dispersed. This allows rapid colonization of favorable environments. Sexual reproduction, while more complex, involves the fusion of two compatible mycelia, mixing genetic material and creating diversity. This diversity is crucial for adapting to changing conditions, resisting diseases, and evolving new traits. The mushrooms we see are usually the sexual stage, fruiting bodies designed to produce and disperse sexual spores. But many fungi spend most of their lives in the asexual stage, cloning themselves, expanding their networks, and waiting for the right moment to reproduce sexually. This flexibility gives fungi an advantage, allowing them to respond to environmental pressures with the strategy best suited to the moment. Many fungi have complex life cycles with multiple stages. The life cycle of a fungus can be surprisingly intricate. A spore lands on a suitable surface and germinates, growing into a network of hyphae. If conditions are right, this mycelium may eventually produce fruiting bodies, mushrooms, which release spores to begin the cycle again. But in many species, there are additional stages. Some fungi have different forms at different points in their lives, changing shape and function. Rust fungi, which infect plants, can have up to 5 different spore types and may require 2 different host plants to complete their life cycle. These complexities allow fungi to exploit different ecological niches and survive adverse conditions. Understanding these life cycles is essential for managing fungal diseases in agriculture and for appreciating the sophistication of fungal biology. Each stage is a response to environmental challenges, a testament to fungi's evolutionary ingenuity. Some fungi require 2 separate host plants to complete their life cycle. Rust fungi are particularly fascinating in their complexity. Many species cannot complete their life cycle on a single host. They must alternate between 2 different plant species. For example, wheat rust spends part of its life on wheat and part on barberry bushes. The fungus produces different spore types on each host, each adapted to a different role. This requirement for 2 hosts complicates the fungus's life, but also provides advantages, allowing it to exploit different resources and spread more effectively. For farmers, understanding these life cycles is crucial. By removing alternate hosts from the vicinity of crops, they can break the cycle and reduce disease. The complexity of these rust fungi, with their multiple spore stages and host requirements, reveals the intricate evolutionary dances that occur in ecosystems, where fungi, plants, and environment are all intertwined in relationships built over millions of years. Bracket fungi grow on trees and can live for decades. On the trunks and branches of trees, you often see shelf-like growths, layered and woody. These are bracket fungi, also called polypores. Unlike the soft mushrooms that appear and disappear quickly, bracket fungi can persist for years or even decades. They grow slowly, adding a new layer each year, much like tree rings. Some become enormous, several feet across, and incredibly heavy. Bracket fungi are decomposers, breaking down the wood they grow on. Some are parasites, attacking living trees and eventually killing them. Others are saprotrophs, colonizing dead wood and recycling it back into the ecosystem. Their hard, woody texture makes them inedible to most animals, and their longevity means they become permanent features of the trees they inhabit. To see an old bracket fungus is to witness years of slow, steady growth, a testament to the patience and persistence that characterize so much of the fungal kingdom. Fungi can break down toxic chemicals in contaminated sites. Mycomediation, the use of fungi to clean up pollution is a growing field. Fungi have been used to degrade pesticides, herbicides, industrial solvents, and even explosives. Their enzymes are non-specific, meaning they can break down a wide range of chemicals, not just natural organic matter. In sites contaminated with petroleum products, fungi can reduce hydrocarbon concentrations significantly. In areas with heavy metals, certain fungi absorb and concentrate the metals in their tissues, which can then be harvested and disposed of safely. This process is slower than some chemical treatments, but it is often cheaper, more sustainable, and less disruptive. Fungi work quietly, spreading through the soil, transforming toxins into harmless substances. As we face legacies of industrial pollution, fungi offer hope. They remind us that nature has tools for healing, that the same processes that decompose a leaf can also dismantle a toxin, returning poisoned land to health. Fungi played a role in the Irish potato famine. Not all fungi are benign. Some cause devastating diseases. In the mid-19th century, a fungus-like organism called Phytophthora infestans, though technically not a true fungus but an oomycete, caused the Irish potato famine. It infected potato crops, causing them to rot in the fields and in storage. Potatoes were the primary food source for much of Ireland's population, and the failure of the crop led to mass starvation, disease, and emigration. Over 1 million people died, and 1 million more fled the country. The famine had profound social and political consequences, shaping Irish history and the Irish diaspora. While Phytophthora is not a fungus, it highlights the immense power organisms like fungi have over human affairs. Crop diseases caused by true fungi continue to threaten food security worldwide. Understanding and managing these diseases is crucial, and it requires respecting the adaptability and resilience of these organisms. Fungal diseases can devastate crops and forests. Fungi are responsible for many plant diseases that affect agriculture and forestry. Dutch elm disease, caused by a fungus spread by bark beetles, has killed millions of elm trees across North America and Europe. Chestnut blight, caused by another fungus, wiped out the American chestnut, once a dominant tree in eastern forests. In agriculture, rusts, smuts, and blights reduce yields and quality. Wheat rust alone has caused famines throughout history. Managing these diseases requires constant vigilance, breeding resistant varieties, applying fungicides, and monitoring for new outbreaks. Fungi evolve rapidly, and what worked to control a disease one year may fail the next. The battle between agriculture and fungal pathogens is ongoing. A reminder that we share this planet with organisms that have their own survival strategies. Fungi do not attack crops out of malice. They are simply doing what they do, exploiting available resources. Our challenge is to coexist, protecting our food while respecting the ecological roles fungi play. Ergot fungus on grains can produce potent toxins. Ergot is a fungus that infects grains, particularly rye. It replaces the grain kernels with dark, hard structures called sclerotia, which contain powerful alkaloid toxins. If contaminated grain is milled into flour and consumed, it can cause ergotism, a condition with symptoms ranging from convulsions and hallucinations to gangrene and death. In medieval Europe, ergotism was known as St. Anthony's fire, and it caused outbreaks of mass illness. Some historians believe ergot poisoning may have played a role in events like the Salem witch trials, where strange behavior and accusations of witchcraft could have been symptoms of ergotism. Today, contaminated grain is usually detected and discarded, but ergot remains a concern in some regions. Interestingly, compounds derived from ergot have medical uses, including treatments for migraines, and as precursors to certain drugs. Ergot is a reminder that the line between poison and medicine is often narrow, and that fungi produce some of the most potent chemicals known. Some fungi produce compounds used in medical imaging. Fungi's chemical diversity extends beyond antibiotics and toxins. Some produce compounds useful in medical diagnostics. For example, certain fungal metabolites are used as contrast agents in imaging procedures, helping doctors visualize tissues and organs. Other compounds are being explored for their fluorescent properties, which could aid in research and diagnostics. The variety of molecules fungi produce is vast. Each evolved for specific ecological functions, but many have found applications in science and medicine. Researchers continue to screen fungi for new compounds, knowing that each species may produce dozens or even hundreds of unique chemicals. Some of these may become the medicines or tools of tomorrow. The fungi growing in a forest or a lab culture may hold answers to questions we have not yet asked, solutions to problems we have not yet solved. Their chemical ingenuity, honed over hundreds of millions of years, is a resource we are only beginning to tap. Fungi are estimated to include millions of undiscovered species. Scientists have described and named about 150,000 species of fungi, but this is likely just a small fraction of the total. Estimates suggest there may be between 2 and 5 million fungal species on Earth, meaning most fungi remain unknown to science. Many live in remote or poorly studied habitats, from tropical rainforests to deep ocean sediments. Others are microscopic, easily overlooked, or difficult to culture in laboratories. Advances in genetic techniques are revealing hidden diversity, showing that what was thought to be a single species is actually many. Each new species discovered adds to our understanding of fungal diversity and ecology. Some may produce novel compounds, offer new insights into evolution, or play unexpected roles in ecosystems. The vast majority of fungi are still out there, waiting to be found. Every forest, every soil sample, every piece of wood holds potential discoveries. The fungal kingdom is far larger and more diverse than we have yet realized. Fungi are essential to nutrient cycling in ecosystems. Without fungi, ecosystems would collapse. Dead plant material would accumulate, nutrients would become locked away, and soil fertility would plummet. Fungi break down complex organic compounds, releasing nitrogen, phosphorus, carbon, and other elements back into forms that plants and other organisms can use. This nutrient cycling is fundamental to life on Earth. In forests, fungi decompose leaf litter, fallen branches, and dead trees. In grasslands, they break down roots and shoots. In wetlands, they process organic material in waterlogged soils. Everywhere, fungi are at work, unseen but essential, turning death into life, closing the loop in the great cycle of nutrients. This role is ancient, and it will continue long after humans are gone. Fungi are patient, persistent, and efficient, the ultimate recyclers, ensuring that nothing is wasted, that every atom returns to the cycle, ready to become part of life again. Some fungi form partnerships with algae in aquatic environments. While lichens are the most famous fungal-algal partnerships, similar relationships exist in water. Some fungi form associations with algae in freshwater and marine environments, though these are less well studied than their terrestrial counterparts. These partnerships allow both organisms to survive in conditions where neither could thrive alone. The algae provide food through photosynthesis, while the fungi offer protection and perhaps help with nutrient uptake. These aquatic partnerships are reminders that cooperation between different forms of life is not limited to land. Wherever life exists, organisms find ways to work together, sharing resources and challenges. The principles that govern terrestrial ecosystems, competition, cooperation, nutrient cycling, also apply underwater, mediated by fungi and other organisms. The more we study, the more we find that fungi are everywhere, adapting to every niche, forming partnerships, and shaping the living world in countless ways. Fungi can survive in the vacuum and radiation of space. In experiments aboard spacecraft and the International Space Station, certain fungi have been exposed to the vacuum of space, extreme temperatures, and high radiation. Some survived, showing remarkable resilience. These tests were designed to understand the limits of life and the possibility of organisms traveling between planets on meteorites, a hypothesis called panspermia. While most organisms die quickly in space, fungi, particularly those that produce resistant spores or have protective pigments like melanin, can endure. This raises intriguing questions. Could life, or at least its building blocks, spread through the solar system on rocks blasted into space by asteroid impacts? Could fungi, or similar organisms, survive a journey from Mars to Earth, or vice versa? While we do not yet know, the resilience of fungi in space suggests that life, once started, might be harder to confine than we think. The same organisms decomposing wood in a forest might, in theory, survive a voyage through the stars. Fungi have inspired art, literature, and folklore for centuries. The mysterious appearance of mushrooms, often overnight, in rings or clusters, has captured human imagination for millennia. Fairy rings were thought to mark places where fairies danced, or where lightning struck, or where dragons rested. Mushrooms appear in folklore as symbols of magic, transformation, and the boundary between the natural and supernatural. In fairy tales, they are homes for sprites or ingredients in potions. In art, they have been depicted in countless forms, from medieval manuscripts to modern illustrations. Writers and poets have used fungi as metaphors for decay, renewal, hidden knowledge, and the uncanny. The fly agaric mushroom, with its iconic red cap, is a staple of fantasy imagery. Fungi occupy a unique place in our culture, familiar yet strange, useful yet dangerous. They remind us that the world is full of mystery, that not everything fits neatly into categories, and that beauty and danger can coexist. Mycelium networks have been compared to neural networks. The structure of mycelial networks, with their branching, interconnected threads, has drawn comparisons to neural networks in brains. Like neurons, mycelial strands transmit signals, though the mechanism is chemical rather than electrical. Research suggests that mycelium can process information, making decisions about where to grow, how to allocate resources, and how to respond to threats. This does not mean fungi are conscious, but it suggests a form of distributed intelligence, where the network as a whole exhibits behaviors that individual hyphae do not. Some scientists study mycelium as a model for understanding decentralized decision-making and problem-solving. Others see potential applications in computing, where mycelial networks could inspire new algorithms, or even biological computers. The comparison is not perfect, but it highlights something profound. Intelligence, or at least intelligent behavior, does not require a brain. It can emerge from simple rules applied across a network, whether that network is made of neurons, mycelium, or code. Fungi can influence soil structure and prevent erosion. Fungi do more than just decompose. They physically bind soil particles together. Mycelial networks weave through soil, creating a web that holds particles in place. This improves soil structure, making it more resistant to erosion by wind and water. In areas where vegetation is sparse, fungi can be crucial to preventing desertification. Some fungi produce sticky substances that glue soil particles into aggregates, improving water infiltration and aeration. Healthy soils are full of fungal hyphae, part of a complex living system. When soil is degraded, fungi decline, and erosion accelerates. Restoring fungi to damaged soils can help rebuild structure and fertility. This is one reason why sustainable agriculture increasingly emphasizes soil health, including maintaining fungal populations. Fungi are infrastructure engineers, building the physical framework that supports plants, animals, and entire ecosystems. Without them, the soil beneath our feet would be lifeless dust, vulnerable to the wind and rain. Some fungi glow brighter when disturbed. Bioluminescent fungi do not glow constantly at the same intensity. Some species brighten when disturbed, perhaps as a response to being touched or damaged. The reason for this behavior is not entirely clear. It may startle predators or attract insects that disperse spores. Whatever the reason, the effect is eerie and beautiful. Imagine walking through a dark forest and accidentally brushing against a glowing log. Suddenly, the light intensifies, flaring up before slowly dimming again. This responsive glow suggests that fungi are not passive but reactive, responding to their environment in ways we are still discovering. Bioluminescence is already mysterious enough, but the fact that some fungi modulate their light adds another layer of complexity. Every detail of fungal biology seems to hold surprises, reminding us how little we truly understand about these ancient organisms. Fungi can produce natural dyes for textiles. Before synthetic dyes, people extracted colors from plants, insects, and fungi. Many mushrooms produce beautiful dyes when boiled with fabric. The colors range from yellows and oranges to greens, browns, purples, and even blues. Each species yields different shades, and the color can vary depending on the water, the fabric, and any additives used. Natural dye enthusiasts and textile artists rediscover these techniques today, seeking sustainable alternatives to synthetic dyes. Fungal dyes are renewable, biodegradable, and often produce subtle, complex colors that synthetic dyes cannot replicate. The process connects people to the land, requiring knowledge of where and when certain mushrooms appear. It is a slow practice, rooted in observation and patience. To wear fabric dyed with fungi is to carry a piece of the forest with you, a color born from the same organisms that rot logs and feed trees, transformed into something beautiful to the eye. Mushrooms have unique textures prized in vegan and vegetarian cuisine. Mushrooms offer something many plant-based foods do not: a meaty texture and umami flavor. This makes them invaluable in vegetarian and vegan cooking. Portobello mushrooms can be grilled like steaks. Shiitake and oyster mushrooms add depth to stir-fries and soups. Dried mushrooms, rehydrated and cooked, concentrate flavor and provide a savory base for broths and sauces. The texture comes from chitin in their cell walls, which gives them a firmness and chew similar to meat. The umami flavor comes from glutamates and other compounds that trigger savory taste receptors. For those reducing or eliminating meat, mushrooms are not just a substitute, but a culinary ingredient in their own right, with flavors and textures that stand on their own. They bridge the gap between the plant and animal kingdoms, offering something unique and satisfying. Truffle dogs can be trained to detect truffles with incredible accuracy. The training of truffle dogs is a specialized skill passed down through generations. Puppies are introduced to the scent of truffles early, often through play, associating the smell with rewards. Over time, they learn to search for that scent in the field, working with their handler to locate buried truffles. A skilled truffle dog can detect fungi buried a foot or more underground, even distinguishing between different species. The bond between hunter and dog is essential, built on trust and clear communication. These dogs work with enthusiasm, tails wagging as they sniff the ground, and their accuracy is remarkable. For truffle hunters, a good dog is invaluable, turning the search from guesswork into a focused effort. Watching a truffle dog work is to see partnership in action, human and animal cooperating, both benefiting, united by the scent of a hidden fungus. Fungi are being studied for carbon sequestration and climate solutions. As climate change accelerates, scientists are looking to fungi for solutions. Mycorrhizal fungi help trees absorb carbon dioxide from the atmosphere and store it in soils. The mycelium itself is made largely of carbon, and when it dies, that carbon can remain in the soil for years or centuries. Some researchers are exploring ways to enhance fungal networks to increase carbon sequestration in forests and farmlands. Others are studying fungi that can break down lignin and cellulose efficiently, potentially turning agricultural waste into stable soil carbon rather than letting it decompose and release carbon dioxide. Fungi may also play a role in restoring damaged ecosystems, helping plants establish and thrive, which in turn captures more carbon. While fungi alone cannot solve climate change, they are part of the solution. Ancient organisms whose ecological roles may help humanity address a modern crisis. The threads beneath our feet may be part of the key to a stable climate. Some fungi produce natural insecticides. Fungi have evolved chemical defenses against insects, and some of these compounds are effective insecticides. Beauveria and Metahizium are fungi that infect and kill insects, and they are used as biological control agents in agriculture and forestry. Sprayed onto crops or released into the environment, these fungi infect pest insects, reducing their populations without the need for synthetic chemicals. The fungi work slowly, but they are specific to insects and generally harmless to other organisms, including humans, birds, and beneficial insects. This makes them a more sustainable option for pest control. Other fungal compounds are being studied for their insecticidal properties, adding to the toolkit available to farmers and foresters. Fungi, which have battled insects for millions of years, have evolved strategies we are only now learning to harness. Their chemical warfare, refined through evolution, offers us alternatives to the broad-spectrum pesticides that harm ecosystems. Endophytic fungi live inside plants without causing disease. Not all fungi that colonize plants are parasites. Some live inside plant tissues without causing harm, and they may even benefit the host. These are called endophytic fungi. They reside in leaves, stems, and roots, often unnoticed. Some produce compounds that deter herbivores or pathogens, protecting the plant. Others help the plant tolerate stress, like drought or nutrient deficiency. The relationship between plant and endophyte can be subtle, and scientists are still uncovering the roles these fungi play. Every plant may host dozens of endophytic species, each potentially influencing the plant's health and ecology. Some endophytes produce bioactive compounds with medical or agricultural potential. They are part of the hidden diversity within every forest, every field, every garden, unseen passengers that shape the lives of the plants they inhabit, reminding us that organisms are not isolated, but are communities, ecosystems within ecosystems. Fungi can alter the flavor and aroma of fruits and other foods. Certain fungi influence the flavor of the foods we eat in subtle ways. Some yeasts and molds, when they colonize grapes, contribute to the flavor complexity of wine. Noble rot, a fungus that infects grapes under specific conditions, is essential to producing some of the world's finest sweet wines. The fungus concentrates sugars and develops unique flavors that winemakers prize. Similarly, certain fungi are used deliberately in the production of artisan foods, aging meats or ripening cheeses, adding depth and character. In other cases, fungi may colonize food unintentionally, altering flavors in ways that can be undesirable, though not always harmful. The relationship between fungi and food is complex, sometimes beneficial, sometimes detrimental. But it highlights fungi's pervasive influence on human life, shaping not just ecosystems, but also culture, cuisine, and the sensory experiences that define our relationship with the world. Puffballs release clouds of spores when disturbed. Puffball mushrooms are round, often white or tan, and grow on the ground or on wood. When mature, their interior transforms into a mass of powdery spores. If you step on a puffball or poke it with a stick, it releases a cloud of spores, a brown or olive-green puff that drifts into the air. This is the mushroom's way of dispersing its spores, using external force rather than wind alone. The cloud can contain millions or even billions of spores. As a child, finding and popping puffballs is a simple delight. But this moment of play is also reproduction in action. Those spores are carried away, settling in new locations, ready to germinate if conditions are right. Puffballs remind us that fungi have evolved countless strategies for spreading their offspring, and that even a playful kick in the woods is part of nature's grand cycle. Giant puffballs can grow larger than a basketball. Among the most impressive mushrooms are giant puffballs, which can grow to enormous sizes. Some reach over a foot in diameter, and occasional specimens exceed 2 feet, resembling beach balls sitting in the grass. A single giant puffball can produce trillions of spores, an almost incomprehensible number. When young, they are white and firm, and they are edible, with a mild flavor. Many foragers seek them out as a culinary prize. As they mature, the inside turns to spore powder, and the mushroom becomes inedible. Giant puffballs are impressive not just for their size, but for their reproductive potential. That a single fruiting body can release so many spores speaks to the scale of fungal reproduction, the scattershot approach that ensures survival despite overwhelming odds. To find a giant puffball is to encounter abundance, nature's extravagance made visible. Stinkhorn fungi attract flies with foul-smelling slime. Not all fungi rely on wind to spread their spores. Stinkhorn mushrooms use a different strategy. They produce a foul-smelling slime that covers their spore-bearing surface. The odor, often compared to rotting meat, attracts flies and other insects. The insects land on the mushroom, attracted by the smell, and the sticky slime clings to their bodies. As they fly away, they carry spores with them, depositing them in new locations. The stinkhorn's appearance is often bizarre, with phallic or lattice-like shapes that seem almost alien. Despite their smell, stinkhorns are harmless and fascinating examples of evolutionary ingenuity. Fungi have adapted to their environment in countless ways, and stinkhorns show that beauty is not the only path to reproductive success. Sometimes, the best strategy is simply to smell like death and let the flies do the work. Bird's nest fungi resemble tiny nests holding eggs. Among the most charming mushrooms are bird's nest fungi, small cup-shaped structures that look remarkably like miniature bird nests. Inside the cup are round structures called peridiales, which resemble eggs. These peridiales contain spores. The fungi rely on raindrops to spread them. When a raindrop hits the cup, it splashes the peridiales out, sometimes launching them several feet. Some species have a sticky thread attached to the peridial, which helps it adhere to surfaces. This ingenious mechanism uses the force of rain to disperse spores, a passive yet effective strategy. Bird's nest fungi are tiny, often overlooked, but they are marvels of design, showing that fungi have evolved an astonishing variety of reproductive strategies, each suited to their environment. To find one is to glimpse nature's creativity, miniature architecture built by a fungus to ensure its future. Earth stars are fungi that open like flowers when mature. Earth star fungi begin as round, closed structures, but as they mature, the outer layer splits and peels back, forming a star shape with the spore-bearing sac in the center. This opening helps elevate the spore sac and increases the chances of spores being dispersed by wind or rain. The star-like shape is striking, often symmetrical and geometric, appearing almost artificial. Earth stars are found in forests, sandy soils, and other habitats, and they remain on the ground long after releasing their spores, becoming dry and papery. They are reminders that fungi come in forms we might not expect, shapes that challenge our assumptions about what a mushroom should look like. Each species of fungi has evolved a form suited to its needs, and the diversity of these forms is part of what makes the fungal kingdom so endlessly fascinating. Fungi help plants tolerate environmental stress. Mycorrhizal fungi do more than just provide nutrients. They also help plants cope with stressful conditions. In drought, fungal hyphae extend far into the soil, accessing water beyond the reach of plant roots. In salty soils, fungi can help buffer the plant from excess salts. In contaminated soils, some fungi absorb heavy metals, preventing them from harming the plant. Plants with healthy fungal partners are often more resilient, better able to survive harsh conditions. This partnership is especially important in a changing climate, where plants face increasing stress from heat, drought, and altered growing conditions. By supporting mycorrhizal fungi through practices like reduced tillage and avoiding excessive fungicides, we can help plants thrive. The health of our crops, forests, and gardens depends in part on the invisible threads in the soil, the fungi that have supported plants for hundreds of millions of years. Some mushrooms change color when bruised or cut. Many mushrooms undergo color changes when damaged. Some turn blue or green when bruised, a reaction caused by the oxidation of certain compounds. Others release colored latex when cut, like the milk-cap mushrooms that exude blue, orange, or white liquid. These color changes can be useful for identification, helping foragers distinguish between species. But they also hint at the complex chemistry within fungi, compounds that react with air or change under stress. Some of these compounds have defensive roles, deterring predators or inhibiting competitors. Others may simply be byproducts of metabolism. Whatever their function, these color changes are beautiful in their own right, little chemical fireworks happening in real time. They remind us that fungi are not inert but dynamic, full of reactions and transformations, living chemistry unfolding in the forest. Mushrooms can grow on surprising substrates, from coffee grounds to cardboard. Fungi are not picky about their food source. Mycelium can colonize a wide range of organic materials. Home mushroom growers cultivate oyster mushrooms on used coffee grounds, straw, cardboard, and even old books. This versatility makes mushroom cultivation accessible and sustainable. Agricultural and industrial waste can be turned into food or other valuable products through fungi. The same processes that decompose a fallen tree can be harnessed to recycle waste, turning what would be discarded into something useful. This potential has led to interest in urban mushroom farming, where fungi are grown on local waste streams, producing food while reducing landfill contributions. It is a closed-loop system, where waste becomes input, And fungi are the transformers, turning the unwanted into the valuable. The simplicity and efficiency of fungal decomposition offer lessons for how we might design more sustainable systems. Mushroom spores are used in forensic science. In some criminal investigations, fungal spores found on evidence can provide clues. Because different environments support different fungi, the species present can indicate where an object or person has been. Spores cling to clothing, shoes, and surfaces, leaving a microscopic trail. Forensic mycologists analyze these spores, identifying species and sometimes narrowing down locations. This is a niche application, but it highlights the ubiquity of fungi. They are everywhere, leaving traces, colonizing surfaces, releasing spores. Even in the most sterile human environments, fungal spores are present, carried on air currents, waiting for conditions to grow. This invisible presence makes fungi useful in ways that go beyond ecology and medicine, even aiding justice. The kingdom of fungi touches every part of our world, seen and unseen, in ways we are still discovering. Some ancient cultures used fungi as tinder for starting fires. Before matches and lighters, starting a fire required skill and the right materials. Some fungi, particularly bracket fungi with dry, fibrous flesh, were prized as tinder. When struck with a spark, they would smolder slowly, holding the ember long enough to be transferred to kindling. The Iceman, a mummy from over 5,000 years ago found in the Alps, carried pieces of a fungus called Fomes fomentarius, likely for fire starting. This fungus, also known as tinder fungus, was used across Europe and Asia. It could also be processed into a soft material used for clothing or medicinal purposes. These ancient uses show that humans have long recognized fungi's practical value, harvesting them not just for food or medicine, but as essential tools for survival. Fungi were part of the toolkit that allowed humans to thrive in diverse environments. Fungi have been found in permafrost, dormant for thousands of years. In the frozen soils of the Arctic, fungi lie dormant, waiting. When permafrost is thawed and samples are cultured, viable fungi have been recovered, some potentially thousands of years old. These organisms survived freezing, desiccation, and the passage of millennia. When conditions improved, they resumed growth, as if no time had passed. This resilience is staggering. It suggests that fungi can endure conditions that would destroy most life, lying in suspended animation until the world changes. As climate change thaws permafrost, these ancient fungi are awakening, re-entering ecosystems after eons of dormancy. What they will do, whether they will compete with modern species or integrate peacefully, remains to be seen. Their emergence is a reminder that the past is not always past, that dormant life can return, and that the world beneath the ice holds secrets we are only beginning to uncover. Fungi are being explored for creating biodegradable plastics. The plastic pollution crisis has driven scientists to seek alternatives, and fungi are offering promising solutions. Mycelium can be used to create materials that mimic plastic, but are fully biodegradable. By growing mycelium in molds with agricultural waste, companies produce packaging, insulation, and even furniture. These materials are lightweight, strong, and when discarded, they break down naturally, feeding back into the soil. Some researchers are developing fungal-based polymers that could replace petroleum-based plastics in a wider range of applications. The vision is a future where disposable items are grown rather than manufactured, where waste is not a problem because everything returns to the earth. This would require rethinking production and consumption, but fungi offer a path. They have been decomposing the world for millions of years. Now we are learning to use that ability to build a more sustainable future. Mycelium grows at different rates depending on environmental conditions. Temperature, moisture, nutrients, and oxygen all influence how fast mycelium grows. In ideal conditions, some species can expand several inches per day. In poor conditions, growth slows to a crawl or stops entirely. This flexibility allows fungi to respond to their environment, growing quickly when resources are abundant, and conserving energy when times are tough. Mycelium can also enter dormancy, surviving long periods without growing, only to resume when conditions improve. This adaptability is key to fungi's success across diverse habitats. Whether in the heat of a desert or the cold of a tundra, fungi find ways to persist. Their growth is not a steady march, but a rhythm, speeding and slowing with the changing world. Understanding these rhythms is essential for cultivating fungi, managing diseases, and appreciating their role in nature. Fungi form mutualistic relationships with many organisms beyond plants. While the partnership between fungi and plants is the most famous, fungi form beneficial relationships with many other organisms. Some insects cultivate fungi as food, farming them much like humans farm crops. Leafcutter ants, for example, harvest leaves and feed them to a fungus they tend in underground gardens. The fungus breaks down the leaves, and the ants eat the fungal growth. Termites have similar relationships with fungi, and these partnerships have existed for millions of years. Fungi also form associations with certain bacteria, algae, and even other fungi. These mutualistic relationships show that cooperation is a powerful evolutionary strategy. In a competitive world, organisms that work together often thrive more than those that go it alone. Fungi are masters of partnership, forming alliances that benefit both parties and shape ecosystems in profound ways. Leafcutter ants farm fungi in vast underground colonies. Leafcutter ants are among nature's most sophisticated farmers. They cut pieces of leaves and flowers, carry them back to their nests, and chew them into a pulp. This pulp is used to feed a fungus that the ants cultivate in sprawling underground chambers. The fungus grows on the pulp, breaking down the plant material and producing nutritious structures that the ants eat. The ants care for their fungal gardens meticulously, removing debris, regulating temperature and humidity, and even using antibiotics produced by bacteria they carry to protect the fungus from disease. This relationship is ancient, dating back millions of years, and it is obligate. The ants cannot survive without their fungus, and the fungus, bred over generations, depends on the ants. It is a partnership that rivals human agriculture in complexity, a testament to the evolutionary power of cooperation. Termites also cultivate fungi as a primary food source. In tropical regions, certain termites build massive mounds and cultivate fungi within them. Like leafcutter ants, these termites chew plant material, often wood and grasses, and use it to feed a fungus. The fungus grows in specialized chambers within the mound, and the termites harvest and eat the fungal fruiting bodies. The termites cannot digest cellulose on their own, but the fungus can, breaking it down and making nutrients available. This partnership allows termites to exploit a food source, wood, that few other animals can use efficiently. The fungus, in turn, benefits from a constant supply of food and ideal growing conditions. These termite mounds, some taller than a person, are monuments to this ancient collaboration, structures built and maintained by millions of insects to support their fungal partners. It is a relationship that has shaped ecosystems, influencing plant communities and nutrient cycles across vast areas. Some beetles carry fungi to help their larvae develop. Ambrosia beetles bore into wood and introduce fungi into the tunnels they create. The fungi colonize the wood, breaking it down and producing nutrients. The beetle larvae feed on this fungus, not on the wood itself. The beetles carry fungal spores in special structures on their bodies, ensuring that each new tunnel is inoculated. This relationship benefits both. The beetle larvae get a nutritious food source, and the fungus gets dispersal and a new substrate to colonize. These partnerships have evolved independently in several beetle lineages, showing that farming fungi is a strategy that works across different groups of insects. The beetles and their fungi are locked in a co-evolutionary relationship, each shaping the other's evolution. The tunnels beneath the bark of a dead tree are not just galleries carved by insects, but farms, carefully tended ecosystems in miniature. Fungi were among the first organisms to colonize land. Long before plants or animals walked on solid ground, fungi may have been there. Fossil evidence suggests fungi existed on land over 1 billion years ago, possibly even earlier. They would have lived in moist environments, perhaps along shorelines or in shallow soils, slowly adapting to terrestrial life. When plants finally made the move from water to land around 470 million years ago, fungi were already present, and the two groups formed partnerships that were crucial to greening the planet. Without fungi to help gather nutrients and water, early plants would have struggled. The colonization of land by life was a joint effort, and fungi were pioneers in that great transition. Their ancient presence on land shaped the evolution of ecosystems, making possible the forests, grasslands, and all terrestrial life that followed. Every step we take on solid ground is made possible by fungi's ancient arrival. Fossilized fungi have been found in ancient rocks dating back hundreds of millions of years. Paleontologists have discovered fossilized fungal hyphae and spores in rocks from the Ordovician period, over 400 million years ago. Some fossils show fungi associated with early plant roots, evidence of ancient mycorrhizal relationships. Other fossils reveal fungi decomposing organic material, playing the same role they do today. These ancient fungi looked remarkably similar to modern species, suggesting that the basic fungal body plan is highly successful and has changed little over hundreds of millions of years. Finding these fossils helps scientists understand when and how fungi evolved, how they interacted with other organisms, and how they contributed to the development of terrestrial ecosystems. Each fossilized thread or spore is a link to the deep past, a reminder that fungi have been part of life on Earth for an almost unimaginable span of time. Some fungi produce antibiotics that protect themselves from bacteria. Fungi and bacteria often compete for the same resources, and fungi have evolved chemical weapons to defend themselves. Penicillin is the most famous example, but many other antibiotics are produced by fungi. These compounds inhibit or kill bacteria, giving the fungus an advantage in its environment. This arms race between fungi and bacteria has been going on for millions of years, driving the evolution of ever more sophisticated chemical defenses and resistances. When Alexander Fleming discovered penicillin, he was observing this ancient conflict. The mold in his petri dish was simply doing what it had evolved to do, protecting itself from bacterial competitors. Humans have harnessed these fungal defenses to save countless lives, but the battle between fungi and bacteria continues in soils, on surfaces, and in every environment where the two coexist. It is a struggle that has shaped the evolution of both groups and given humanity some of its most important medicines. Fungi can degrade lignin, one of the toughest natural materials. Lignin is a complex polymer that strengthens plant cell walls, giving wood its toughness. It is one of the most abundant organic compounds on Earth, but very few organisms can break it down. Fungi, particularly white rot fungi, have evolved enzymes that can degrade lignin, a remarkable feat. These enzymes are powerful and non-specific, capable of breaking bonds that resist most other biological processes. This ability is crucial for nutrient cycling, allowing carbon locked in wood to be released back into the ecosystem. Scientists are studying these enzymes for industrial applications, hoping to use them to process plant biomass for biofuels, pulp and paper production, and waste treatment. Understanding how fungi break down lignin could lead to more efficient, sustainable processes that replace harsh chemical treatments. The same enzymes that rot a log in the forest might one day power our industries. Fungal spores can travel across continents on wind currents. Spores are so small and light that they can be carried by wind currents for thousands of miles. Studies have found fungal spores in the upper atmosphere, traveling across oceans and continents. A spore released in Africa might land in South America, or one from Asia might reach North America. This long-distance dispersal means fungi can colonize new areas quickly when conditions are right, and it explains why some fungal species are found worldwide. It also means that fungal diseases can spread rapidly, jumping continents, and affecting crops or forests far from their origin. Tracking these airborne spores helps scientists predict disease outbreaks and understand fungal ecology. The air we breathe is full of these travelers, invisible passengers on the wind, each one a potential new beginning, a seed of life waiting for the right place to land. Some fungi are parasites that weaken or kill their hosts. Not all fungal relationships are beneficial. Many fungi are parasites, living off other organisms and harming them in the process. Parasitic fungi infect plants, animals, and even other fungi. Some cause minor damage, while others are lethal. Chestnut blight, Dutch elm disease, and white nose syndrome in bats are all caused by parasitic fungi. These parasites have evolved strategies to invade hosts, evade defenses, and extract nutrients. For the host, the consequences can be devastating. Entire populations of trees, crops, or animals can be decimated by fungal disease. Managing these parasites requires understanding their biology, often developing resistant varieties or treatments to control outbreaks. Parasitic fungi remind us that fungi, like all organisms, are trying to survive, and sometimes survival means exploiting others. It is part of nature's complexity, neither good nor evil, but simply the way life unfolds. White nose syndrome has killed millions of bats in North America. White nose syndrome is a fungal disease that has devastated bat populations across North America. The fungus, Pseudogymnoascus destructans, grows on the skin of hibernating bats, particularly on their noses and wings. It disrupts their hibernation, causing them to wake frequently and deplete their energy reserves. Many bats starve or freeze before spring arrives. The disease has killed millions of bats since it was first detected in 2006, and some species have declined by over 90%. The loss of bats has ecological consequences. Bats are major predators of insects, and their decline has led to increases in pest populations, affecting agriculture and forests. Efforts are underway to understand the fungus, develop treatments, and protect remaining populations. White nose syndrome is a reminder of how a single organism, a fungus, can alter ecosystems, and how interconnected life is. Honey fungus can be both parasite and decomposer. Honey fungus, our malaria species, is one of the most fascinating and troublesome fungi. It can live as a parasite, attacking living trees and causing root rot, or as a saprotroph, decomposing dead wood. Some armillaria species are highly aggressive, killing large trees and spreading through forests via underground rhizomorphs, root-like structures that can extend for meters. Other species are less aggressive and primarily decompose already dead material. The honey mushrooms that fruit in the fall are the visible signs of this fungus, which otherwise lives hidden beneath the bark and in the soil. Armillaria's dual lifestyle shows that the line between parasite and decomposer is not always clear. The same fungus can play different roles depending on circumstances, attacking when weak trees are available, and decomposing when only dead wood is present. It is opportunistic, adaptable, and incredibly persistent. Fungi can communicate warnings about insect attacks through mycelial networks. Research suggests that trees under attack by insects can send chemical signals through mycorrhizal networks to neighboring trees. These neighboring trees then increase their production of defensive compounds, preparing for possible attack. The fungal network acts as a conduit, allowing trees to share information. This phenomenon, sometimes called talking trees, is still being studied, and the mechanisms are not fully understood, but it suggests that forests are far more connected and communicative than previously thought. The mycelium is not just a nutrient highway, but an information network, linking individuals into a community that can respond collectively to threats. This kind of communication challenges our understanding of plants as passive organisms. Mediated by fungi, they become active participants in a complex, interconnected system where the well-being of one affects the survival of many. Mycorrhizal networks can connect trees of different species. The fungal networks in forests are not species-specific. A single mycelial network can connect trees of different species, forming a web that spans the diversity of the forest. This means nutrients and signals can flow not just within a species, but across species boundaries. A fir tree might be linked to a birch, and through them to a pine. This interconnection has implications for forest ecology. It means that diversity may enhance the resilience of forests, with different species supporting each other through shared fungal networks. It also complicates the notion of competition. While trees of different species compete for light and space above ground, below ground they may be cooperating, sharing resources through a common fungal partner. The forest floor is a commons, a shared space where fungi mediate relationships and where the boundaries between individuals and species blur. Some fungi create mycorrhizal associations with orchids. Orchids, with their often spectacular flowers, have a secret. Many cannot germinate without fungi. Orchid seeds are tiny, containing minimal nutrients. When they land, they must immediately form a partnership with a fungus that provides sugars and nutrients until the seedling can photosynthesize on its own. Some orchids remain dependent on fungi throughout their lives, never producing chlorophyll, living entirely off nutrients obtained from their fungal partners. These relationships are highly specific, with each orchid species often partnering with only one or a few fungal species. This dependency makes orchids vulnerable. If their fungal partner disappears, they cannot reproduce. Conservation efforts for rare orchids must consider not just the plants, but their fungal partners, protecting the invisible threads that sustain these beautiful flowers. It is another reminder that what we see is only part of the story, and that survival often depends on unseen relationships. Fungi play a role in the formation of some gemstones and minerals. In certain environments, fungi contribute to mineral formation. Through their metabolic processes, fungi release organic acids that dissolve minerals from rocks. In some cases, these dissolved minerals precipitate in new forms, contributing to mineral deposits. Fungi have been found in association with formations of calcite, silica, and even metallic minerals. While they are not the primary drivers of gemstone formation, they can influence the local chemical environment in ways that promote crystallization. This role is subtle and often overlooked, but it highlights fungi's ability to shape their environment at a chemical level. The earth beneath our feet is not just geology, but a living system, where organisms like fungi interact with rocks and minerals, slowly transforming the inorganic world through their life processes. Some fungi have been used in traditional medicine for thousands of years. Long before modern pharmaceuticals, people turned to fungi for healing. In China, reishi mushrooms have been used for over 2,000 years, believed to promote longevity and vitality. Turkey tail, another polypore, has been used in traditional medicine across Asia. In Europe, birch polypore was used for digestive issues and has been found with the Iceman mummy, suggesting its use over 5,000 years ago. Indigenous peoples around the world have used various fungi to treat wounds, infections, and other ailments. While not all traditional uses have been validated by science, some have. Compounds from these fungi are now being studied and, in some cases, incorporated into modern medicine. These traditional practices represent centuries of observation and experimentation, a body of knowledge that modern science is only beginning to fully appreciate and understand. Turkey tail fungus is being studied for cancer treatment support. Turkey tail, Trametes versicolor, is a colorful bracket fungus, common on dead wood. It has been used in traditional Asian medicine for centuries, and modern research is exploring its potential in cancer therapy. Compounds extracted from turkey tail, particularly polysaccharides, have been shown to support the immune system. In some countries, extracts are used alongside conventional cancer treatments to help boost immune function and improve outcomes. While turkey tail is not a cure, and it should not replace standard treatments, research suggests it may have a role as a complementary therapy. Clinical trials are ongoing. The interest in turkey tail is part of a broader exploration of medicinal fungi, looking to traditional knowledge and modern science to find new tools for health. A fungus that grows on dead logs may hold keys to supporting life, a reminder of nature's complexity and potential. Fungi are essential to the brewing industry. Without fungi, specifically yeasts, there would be no beer, wine, or spirits. Yeasts ferment sugars into alcohol and carbon dioxide, a process humans have harnessed for millennia. Different yeast strains produce different flavors, and brewers and winemakers carefully select and cultivate yeasts to achieve desired results. Wild yeasts give rise to spontaneously fermented beers and natural wines, each batch unique, shaped by the local fungal population. The science of fermentation is ancient, but it remains an art, a collaboration between human and fungus, each bringing something essential. The next time you enjoy a drink, consider the yeast that made it possible. Tiny fungi working quietly, transforming sugars into something humans have valued for thousands of years. A gift from the fungal kingdom that has shaped cultures and celebrations across the world. Some mushrooms are bioluminescent only at certain life stages. Bioluminescence in fungi is not always constant. Some species glow only when young, their light fading as they mature. Others glow only under specific conditions, when disturbed, or when the mycelium is actively growing. The timing and intensity of bioluminescence vary, adding to the mystery. Scientists are still working to understand why these patterns exist. It may be that the light serves different functions at different stages, attracting spore dispersers when the mushroom is ready to reproduce, or deterring predators when the fungus is vulnerable. Whatever the reasons, the variability makes bioluminescent fungi even more intriguing. They are not simply glowing all the time, but responding to their environment and their developmental stage, adding another layer of complexity to an already fascinating phenomenon. Fungal infections in humans are usually surface level, not systemic. While fungi can cause disease in humans, most infections are superficial, affecting the skin, nails, or mucous membranes. Athlete's foot, ringworm, and yeast infections are common examples, caused by fungi that thrive in warm, moist environments. These infections are usually more annoying than dangerous and can be treated with antifungal medications. Systemic fungal infections, where fungi invade internal organs, are rare and typically occur in people with weakened immune systems. For healthy individuals, fungi pose little threat. This is because our immune systems and body temperature are generally effective defenses against fungal invasion. Fungi are adapted to cooler environments, and the warmth of the human body makes it difficult for most species to grow. While fungal diseases exist, they are not the primary threat to human health that bacteria and viruses are. Most of the time, fungi are beneficial or neutral, and we coexist peacefully. Some fungi live in extreme heat, like hot springs. While many fungi prefer moderate temperatures, some thrive in extremes. In hot springs, where water temperatures can exceed 140 degrees Fahrenheit, thermophilic fungi have been discovered. These organisms have adapted to the heat, their enzymes and cellular structures modified to remain stable at high temperatures. Studying these fungi provides insights into the limits of life and offers potential industrial applications. Enzymes that work at high temperatures are valuable for processes like industrial baking, brewing, and biofuel production. The discovery of extremophile fungi expands our understanding of where life can exist and what conditions it can tolerate. Whether in boiling water, frozen tundra, or radioactive zones, fungi demonstrate resilience and adaptability, colonizing niches that seem inhospitable, reminding us that life is creative and persistent, finding ways to thrive in the most unlikely places. Mushrooms contain compounds that may boost immune function. Beyond their nutritional value, mushrooms contain bioactive compounds that may support health. Beta-glucans, polysaccharides found in many mushrooms, have been shown to modulate immune responses, potentially enhancing the body's ability to fight infections and disease. Other compounds in mushrooms have antioxidant properties, helping to protect cells from damage. While more research is needed, and mushrooms are not miracle cures, they are increasingly recognized as functional foods, offering benefits beyond basic nutrition. Traditional medicine systems have long valued certain mushrooms for health, and modern science is beginning to validate some of these uses. Including mushrooms in your diet may contribute to overall wellness, a simple step that connects you to ancient practices and the natural world. Every meal can be an opportunity to partner with fungi, just as forests partner with mycelium, a quiet collaboration that sustains life. Fungi are used in the production of citric acid and other food additives. Many food additives and flavor enhancers are produced using fungi. Citric acid, widely used in beverages, candies, and as a preservative, is largely produced by fermenting sugars with the fungus Aspergillus niger. Other enzymes and acids used in food processing also come from fungi. This industrial fermentation is efficient and scalable, providing ingredients for the global food industry. Fungi work in stainless steel tanks, fed sugars and nutrients, producing the compounds we need. It is a far cry from a mushroom in a forest, but it is the same fundamental process: fungi consuming and transforming, breaking down and building up. The invisible hand of fungi shapes not just ecosystems, but economies, industries, and the very food we eat. They are partners in ways we rarely acknowledge, essential to modern life. Mushroom foraging has become a popular hobby and connects people to nature. In recent years, more people have taken up mushroom foraging, drawn by the combination of outdoor activity, learning, and the possibility of culinary rewards. Foraging requires patience, observation, and knowledge, making it a mindful practice. It connects people to the seasons, to local ecosystems, and to the rhythms of nature. Each outing is different, shaped by weather, location, and chance. The hunt for mushrooms becomes a form of meditation, a slow walk through the woods with attention focused on the ground, the logs, the subtle signs of fungal life. For many, foraging is not just about the mushrooms, but about the experience, the quiet time in nature, the sense of discovery, and the connection to something ancient. It is a practice that requires respect for the land, for the fungi, and for the knowledge needed to forage safely and sustainably. Fungi inspire biomimicry in engineering and design. The structure of mycelium, its branching networks and efficient resource distribution, has inspired engineers and designers. Mycelial networks optimize connections, balancing efficiency and resilience, lessons that can be applied to designing communication networks, transportation systems, and supply chains. The way fungi decompose materials has inspired waste management strategies. The strength and lightness of fungal structures have led to innovations in materials science. Biomimicry, the practice of learning from and imitating nature, sees fungi as models for solving human problems. By studying how fungi grow, communicate, and adapt, we can develop technologies that are more sustainable, efficient, and harmonious with natural systems. Fungi have been solving problems for millions of years, and we are learning to listen, to observe, and to apply their solutions to our own challenges. In doing so, we honor the ingenuity of the natural world and find paths toward a more sustainable future. Some mushrooms are used in natural dyeing for vibrant, lasting colors. Natural dyers prize mushrooms for the colors they produce, which can be surprisingly vibrant and light-fast. Unlike some plant dyes that fade quickly, fungal dyes often last well with proper treatment. The process of dyeing with mushrooms connects the dyer to the fungi, to the forest, and to traditional crafts. Each dyeing session is unique, influenced by the species used, the water chemistry, and the fabric. The colors range from subtle earth tones to bright yellows and deep purples. Some dyers forage their own mushrooms, while others cultivate them or purchase them. The practice is part art, part science, and part reverence for the natural world. To wear fabric dyed with fungi is to carry a piece of the forest, a reminder of the beauty that arises from decomposition, from the quiet work of organisms transforming the world molecule by molecule. Fungi can help restore degraded land through mycomediation. In areas damaged by pollution, erosion, or overuse, fungi can play a role in restoration. Mycomediation involves introducing fungi to contaminated or degraded sites to help break down toxins, stabilize soil, and support plant regrowth. Fungi can also help rebuild soil structure, increasing its ability to hold water and nutrients. In some cases, fungi have been used to restore sites after oil spills, industrial contamination, or mining. The process is slow and requires careful management, but it offers a natural, low-cost approach to healing damaged land. By partnering with fungi, we can help ecosystems recover, restoring health and function to places that have been harmed. It is a form of collaboration, working with nature rather than imposing solutions from outside, allowing the organisms that have always done this work to do it again, supported and guided by human care. Fungal mycelium has been used to create sustainable alternatives to styrofoam. Mycelium-based materials are being developed as replacements for styrofoam and other petroleum-based products. Agricultural waste is mixed with mycelium, which binds it together as it grows. The resulting material is lightweight, insulating, and fully compostable. Companies are using it for packaging, shipping materials, and even insulation in buildings. At the end of its life, instead of sitting in a landfill for centuries, mycelium packaging can be composted, returning nutrients to the soil. This approach represents a shift from extraction and waste to growth and renewal. Materials are not manufactured from finite resources, but grown from waste, using biological processes. Mycelium packaging is still in its early stages, but it points toward a future where our materials are living, biodegradable, and aligned with natural cycles. Fungi, once again, offer solutions, this time to the problem of waste, turning what we discard into the foundation for what we need. The smell of rain on soil, petrichor, is partly due to fungi. That earthy, fresh smell that rises after rain, the scent we call petrichor, comes in part from fungi and bacteria in the soil. They release compounds, including geosmin, which are carried into the air by raindrops hitting the ground. This aroma is deeply linked to human experience, evoking memories and emotions. It tells us the earth is alive, that unseen processes are unfolding beneath our feet. The smell is a signature of life, of growth and decay, of the cycles that sustain ecosystems. Every time it rains, and that scent rises, fungi are part of the story, their chemical voices carried on the breeze, invisible yet profoundly present. The smell of rain is the smell of the living earth, and fungi are integral to that ancient grounding aroma. Fungi form part of the gut microbiome in some animals. While bacteria dominate most animal gut microbiomes, fungi also play a role. In humans, the gut microbiome includes yeasts and other fungi, and research is beginning to explore their influence on health. In ruminants like cows, anaerobic fungi help break down tough plant fibers, contributing to digestion. The balance of fungi in the gut can affect immunity, metabolism, and overall health. Disruptions to the microbiome may be linked to certain diseases, though research is still in early stages. This hidden fungal community is part of the complex ecosystem within every animal, a reminder that we are not individuals but ecosystems, hosting countless organisms that influence our well-being. Fungi, once again, are partners, living within us, shaping our biology in ways we are only beginning to understand. Mushrooms can fruit in winter, even pushing through snow. While many mushrooms appear in the warmer months, some species fruit in winter. These cold weather mushrooms are adapted to low temperatures and can even push through snow. The oyster mushroom, for example, often fruits in late fall and winter. The velvet foot mushroom thrives in cold weather, its name referring to its fuzzy stem. These mushrooms take advantage of reduced competition and different ecological conditions. Foragers who venture out in winter can find treasures that others miss, a reminder that the fungal world does not shut down completely in cold months. Life continues, adapted to the season, quietly fruiting beneath the snow, waiting for the observant eye. The resilience and adaptability of fungi are on display even in the depths of winter, proving that life finds a way, no matter the season. Fungi inspire wonder and curiosity across cultures. Throughout human history, fungi have fascinated us. Their sudden appearance, strange forms, and sometimes potent effects have made them subjects of myth, medicine, and study. In every culture, people have noticed mushrooms, given them names, and woven them into stories. Some cultures revere them, others fear them, but none ignore them. Fungi occupy a space between the familiar and the alien, the useful and the dangerous. They challenge our categories, being neither plant nor animal, growing in darkness, transforming death into life. This liminality makes them powerful symbols, representing transformation, mystery, and the interconnectedness of life. As science reveals more about fungi, their role in ecosystems, their biochemical complexity, and their potential for solving human problems, our fascination only deepens. Fungi remind us that the world is full of wonders, that much remains unknown, and that paying attention to the small and overlooked can lead to profound discoveries. And so, dear listener, our journey through the hidden world of fungi comes to a close. From the vast underground networks that connect forests to the tiny spores drifting on the wind, from the mushrooms that push through the earth overnight to the ancient partnerships that allowed plants to colonize land, we have wandered together through a kingdom as old as time. We have glimpsed the bioluminescent glow of foxfire, tasted the transformation of fermentation, and marveled at the resilience of organisms that thrive in the harshest conditions. We have seen fungi as decomposers, healers, builders, and partners, shaping the world in ways both visible and invisible. The fungal kingdom reminds us that life is interconnected, that beauty and decay are part of the same cycle, and that the smallest organisms often play the largest roles. Beneath every forest, every garden, every patch of soil, fungi are at work, quietly transforming, connecting, sustaining. They ask nothing of us, yet they give everything, recycling nutrients, supporting plants, and offering medicines and food. They are teachers, if we take the time to learn, showing us that cooperation is powerful, that resilience is born of adaptability, and that life finds ways to thrive even in darkness. As you lie here, letting your breath fall into an easy rhythm, imagine yourself in a quiet forest. Picture the earth beneath you, rich and alive, threaded with mycelium. See the mushrooms rising in the dappled light, the fallen logs slowly dissolving, and the trees standing connected through an invisible web. Feel the patience of fungi, their slow, persistent growth, their transformation of death into new life, all of it flowing into stillness, into memory, into dreams. The fungi have carried life for hundreds of millions of years, and they will carry it long after we are gone. Their story is not finished, and in learning about them, neither is ours. Just as a spore settles into soil, every thought drifts gently toward rest. If you happen to still be awake, you can go ahead and let yourself drift deeper now. But if your eyes are growing heavy, let the quiet wisdom of fungi hold you. Let the underground network support you and carry you softly into rest. Close your eyes, breathe deeply, and drift into sleep, into stillness, into the vast and timeless silence where fungi themselves keep watch, breaking down, building up, and connecting all of life in an endless, gentle cycle. Good night.